In the deepest darkness, where galaxies should gather, James Webb found something impossible. Ancient black holes burning alone. No fuel, no neighbors, just void. For 20 years, scientists measured the cosmos. They thought they knew the map. They were wrong. We don't live in the universe we thought we did. We live inside a bubble, a pocket of almost nothing, 2 billion light years wide. And it's growing. It's warping everything we measure about reality itself. The James Webb Telescope pointed at a region of space 13 billion light years away and found something that shattered every model we had. 5 ancient quasars, blazing with the power of trillions of stars, floating in what looked like cosmic deserts. These weren't supposed to be here. These objects formed when the universe was barely 430 million years old. Think about that. The universe had barely started, and yet these monsters already existed. Here's the problem. Quasars need supermassive black holes at their cores. Black holes need fuel. Lots of it. Gas, dust, entire galaxies getting consumed by the gravitational beast at the center. Theory said these early quasars would live in the densest neighborhoods of the young cosmos, surrounded by 50 or more companion galaxies, all feeding the fire. It made sense. It followed the rules. Scientists at MIT led the observation campaign in 2024. They examined the cosmic surroundings of each quasar, one by one. Some matched predictions perfectly. Crowded environments, packed with galactic neighbors. Exactly as the models suggested. Then came the others. These quasars drifted in isolation. Only a handful of stray galaxies scattered nearby. No dense environment. No obvious fuel source. Nothing that should have allowed these monsters to exist. Anna Christina Eilers and her team checked their data 3 times, then a 4th time. The findings held. Lonely, supermassive black holes, shining impossibly bright, in regions where they had no right to exist. The telescope's instruments captured clear images. Each observation session revealed the same brutal pattern. Dense quasar fields where expected. Empty quasar fields where impossible. The contradiction forced physicists to confront something uncomfortable. Everything they thought they understood about how black holes grow was wrong. Without surrounding matter to consume, these objects should have stayed small. Instead, they achieved masses millions of times greater than our sun in a cosmic instant. Somehow, impossibly, they fed themselves in the dark. But here's where it gets stranger. The location of these lonely quasars wasn't random. They appeared to inhabit voids, vast regions of space with below-average matter density. Voids existed in the modern universe. Everyone knew that. But finding them in the infant cosmos, already large enough to isolate quasars, that contradicted everything. The universe at that age should have been more uniform. Gravity hadn't had time yet to pull matter into the extreme concentrations and depletions we see today. The structure shouldn't have existed. In October 2024, the team published their findings in the Astrophysical Journal. Their conclusion was cautious, yet unmistakable. These quasars exist in environments that current theory cannot explain. Either black hole growth operates through unknown mechanisms, or the early universe contained structure on scales previously thought impossible. Both possibilities rewrote cosmology. Neither provided comfort, because what Webb found at the edge of the observable universe might also exist right here, wrapped around our own galaxy. Your home galaxy floats inside a bubble of nearly empty space 2 billion light years across. Keenan-Barger-Cowie Void, named after the 3 astronomers who first identified it in 2013, surrounds the Milky Way like an invisible sphere. This isn't speculation. Optical telescopes, infrared surveys, X-ray observations, radio measurements, all of them point to the same conclusion. Our local universe contains 20% less matter than it should. We are not where we think we are. We are passengers in a cosmic bubble, a pocket of almost nothing, drifting through a universe that doesn't match our equations. The implications are just beginning to settle in. The universe has a blind spot, and we're standing in it. Imagine the universe as an archipelago. Galaxies cluster into islands. These islands link together with bridges of matter, forming a vast network that stretches across the entire cosmos. It's called the cosmic web, and it's beautiful. But between these dense filaments, vast empty oceans, voids. Most galaxies live on the islands or the bridges connecting them. We don't. We live in the middle of the ocean. It's called the KBC void, and its discovery is about to shatter everything we thought we knew about how the universe works. For decades, astronomers assumed our cosmic neighborhood was typical, average, unremarkable. Then they started counting. Galaxies at 200 million light years away? Check. 400 million light years? Still checking. 600 million light years? And here's where things got strange. The farther they looked, the fewer galaxies they found nearby. The more galaxies appeared in the distance. This wasn't supposed to happen. The universe should look roughly the same everywhere you stand, but it doesn't. Not from here. Not from Earth. Multiple teams confirmed it independently. The 2-mass redshift survey cataloged over 43,000 galaxies within 380 million light years. Same pattern. The Sloan Digital Sky Survey saw it. The WISE infrared mission saw it too. The evidence was unmistakable. Our cosmic neighborhood is genuinely sparse. We're living in a cosmic desert, a void so massive it ranks among the largest ever detected, and we're sitting near its center. Now here's where it gets weird. We also live inside the Laniakea supercluster, a structure containing 100,000 galaxies, including our Milky Way. How can a supercluster exist inside a void? It's not a contradiction. It's a matter of perspective. Imagine a small island in the middle of the Pacific Ocean. The island is still an island. It's still relatively dense compared to water. But the ocean is so vast, so overwhelmingly empty, that the island remains fundamentally isolated. That's us. That's our supercluster, dense on the inside, but adrift in an ocean of emptiness spanning 2 billion light years. Our location matters more than we realized, because living inside this void doesn't just change our geography, it changes how we measure the universe itself. And right now, the universe is giving us two completely different answers. The Hubble constant. This single number might be the most important measurement in all of science. It tells us how fast the universe is expanding. Not just expanding, how quickly space itself is stretching, carrying galaxies apart like dots on an inflating balloon. This number determines everything. The age of the universe, how dark energy behaves, the entire timeline of cosmic evolution. Get it wrong, and our understanding of reality collapses. But here's the problem. We can't agree on what it is. The first method looks backward in time, ancient light from the cosmic microwave background. Radiation born just 380,000 years after the Big Bang itself. This light carries imprints from the infant universe. Temperature fluctuations frozen into the sky when the first atoms formed. The Planck satellite analyzed these patterns with stunning precision and delivered a number. Approximately 67 kilometers per second per megaparsec. It matches the standard model almost perfectly. The math works. The theory checks out. Problem solved. Except it's not. Because the second method uses nearby galaxies. Astronomers identify Cepheid variable stars that pulse with predictable brightness. By measuring how bright they appear, scientists calculate their distance. Then they use Type 1, a supernovae. Cosmic explosions so consistent, they serve as standard candles across the universe. Adam Rees and his team refined this technique using data from both the Hubble Space Telescope and the James Webb Space Telescope. State-of-the-art precision, multiple independent confirmations, and they got a different answer. Approximately 73 kilometers per second per megaparsec, 10% higher. In casual terms, 10% sounds like rounding error, measurement noise, a minor disagreement between research teams. But in cosmology, 10% is a crisis. It's a red flag the size of Jupiter. Two different methods, both measuring the same thing, both performed by brilliant scientists using cutting-edge technology, both returning fundamentally incompatible results. Something is wrong, and we don't know what. Could it be the void? Our cosmic isolation? Maybe living inside an underdense region skews how we perceive the universe's expansion. Maybe the voids and filaments of the cosmic web warp space itself around us, creating optical illusions that cascade into measurement errors. Maybe the universe doesn't expand uniformly. Maybe gravity's influence varies depending on where you stand, or maybe our theories are incomplete. Maybe dark energy isn't what we think. Maybe the Big Bang's aftermath left scars on space-time we've never accounted for. We're standing on the edge of a profound mystery, and the key to solving it might lie in the simple fact that we're standing in the middle of nowhere at all. The universe's greatest mystery, and why it shatters everything we know. Listen. For decades, astronomers have been measuring the universe. They've built telescopes. They've refined their instruments. They've checked their work obsessively, and something disturbing has happened. The more precise their measurements became, the more they realized something was impossibly, fundamentally wrong. Early on, there was wiggle room. The error bars overlapped. Maybe it was just the instruments. Maybe it was just how we were looking. But then came refinement. Then validation. James Webb looked at the same cosmic distances Hubble had measured decades earlier. The answers matched perfectly, but they contradicted other measurements by a mind-bending margin. Something had to give. The problem? Nothing did. For over a decade now, this cosmic tension has refused to budge. Nobel laureate Martin Rees put it bluntly: the more precise our measurements get, the worse the problem becomes. This isn't measurement error anymore. This is something real. And here's what that means. If local measurements are correct, the universe is roughly 1 billion years younger than we calculated. Galaxy formation timelines collapse. Dark energy, the mysterious force tearing space apart, behaves completely differently than we thought. The entire cosmic story, from the Big Bang to today, needs rewriting. But if the cosmic microwave background is right instead, then something else is happening. Something unknown is accelerating the expansion of the universe in our local region. Something is systematically skewing every distance measurement we make nearby. Either way, we've hit a wall. Our understanding of the universe has a fundamental crack running through it. But what if we've been asking the wrong question? What if the problem isn't how we're measuring? What if it's where we're measuring from? Let's go back, way back. Before atoms existed, before electrons and protons even knew what they were, the early universe was chaos, pure, screaming chaos. A roiling plasma of particles and energy, compressed into temperatures so extreme that light itself was trapped. Photons, electrons, protons, dark matter, all churning together in a superheated fluid so dense, so violent, that nothing could survive it. But something was moving through this madness. Pressure waves, sound waves, essentially. They rippled outward like invisible tsunamis through the cosmic soup, triggered by the tiniest density fluctuations, quantum whispers from the very first moments after creation. As these waves traveled at nearly half the speed of light, they compressed matter in their wake, squeezing it tighter and tighter. Then, at a specific moment in time, exactly 380,000 years after the Big Bang, everything froze. The universe cooled just enough. Electrons and protons finally stopped their frantic dance and merged into hydrogen atoms. Light, which had been trapped and scattered for nearly 400,000 years, broke free. The universe became transparent, and the sound waves? They stopped cold. They were locked in place forever, their cosmic journey complete. But their fingerprints were everywhere. The first place you can see them is in the cosmic microwave background radiation, the ancient afterglow of the Big Bang itself. Look at it closely enough, and you see subtle variations in temperature scattered across the sky. These patterns are the echo of those frozen sound waves. They're still there, imprinted on light that has been traveling toward us for 13.8 billion years. But there's a second, far more important signature, where the sound waves compressed matter. They left behind slightly denser regions. Gravity noticed. Over billions of years, these overdense zones gathered more and more material, pulling galaxies and gas around them like an invisible web. Eventually, they became the cosmic filaments and massive galaxy clusters we see today. And here's the crucial part. The distance between these compressed regions is always the same. Roughly 490 million light-years in our expanded universe today. This distance isn't random. It's written into physics itself. The sound waves could only travel so far in those first 380,000 years before atoms formed. That maximum distance, called the sound horizon, is a cosmic ruler, engraved by fundamental physics itself. And because the universe has expanded by a known amount since then, we can calculate exactly how far apart these regions should be today. Astronomers call this pattern baryon acoustic oscillations, and it's one of the most reliable cosmic measuring sticks we've ever discovered. When you look at distant galaxies and measure their positions, you see something remarkable. They don't scatter randomly. They cluster more densely at specific separations, at multiples of that 490 million light-year scale. The signal is faint when you look at small samples, but gather millions of galaxies together, measure them all, and the pattern screams out at you. For years, this technique has been the gold standard. We've used it to map the universe, to measure how fast space was expanding at different times, to probe the behavior of dark energy itself. The most ambitious effort is called DESI, the Dark Energy Spectroscopic Instrument. It's the most detailed cosmic survey ever attempted. Millions upon millions of galaxies, each one measured, each one mapped, each one telling us how far away it is through something called redshift, how much space has expanded since light left that galaxy. Recently, DESI made an observation. Something unexpected, something that might finally crack open this mystery. And that observation might mean something profound is watching from the void. The universe's most uncomfortable secret. There's a crack in our cosmic map, and it's been staring us in the face for years. We thought we understood the universe. We built a model, elegant, mathematically perfect, that explained how space itself expands, carrying galaxies away from each other like dots painted on an inflating balloon. For decades, it worked. The predictions matched the observations. Science was doing what science does best, predicting reality with stunning precision. Then the measurements started lying. In 2025, astronomers compiled 20 years of data from something called baryon acoustic oscillations. Think of it as the universe's heartbeat, an ancient sound wave frozen in the positions of galaxies, a fossil echo from the Big Bang itself. These measurements should follow a smooth, predictable pattern. They should whisper confirmation of our cosmological model. Instead, they screamed contradiction. At nearby distances, within about 4 billion light years, the universe was expanding faster than it should. The predictions said one thing, the measurements said another. And the difference was not some tiny measurement hiccup. It was systematic, persistent, real. Cosmologists scrambled for explanations. Maybe dark energy was changing over time. Maybe gravity itself worked differently than we thought. Maybe the surveys had hidden errors we hadn't caught. But there was another possibility, one that made most scientists deeply uncomfortable. What if we lived somewhere special? Not special in a metaphorical sense, special in a literal cosmological sense. What if Earth sits inside a massive cosmic void, a region where matter is stretched thinner than average, like standing in an underpopulated corner of an otherwise crowded galaxy? This wasn't a new idea, but it was an idea most researchers had quietly shelved. The universe, we believed, should look the same everywhere. Any other answer felt too close to putting us back at the center of creation. So when researchers from the University of Bonn and St. Andrews actually tested this hypothesis, they expected it to fail. They didn't expect what came next. They took every baryon acoustic oscillation measurement, every data point accumulated over 2 decades, and asked a simple question. What would the universe look like if we lived inside a massive underdense region? Then they compared their predictions to reality. The fit was not close. It wasn't even remarkable in the way good science papers are remarkable. It was staggering. The void models explained the data 100 million times better than the uniform universe model. 100 million times. Let's put that in perspective. In statistics, we usually celebrate when a new theory is 3 times better than the old one. This wasn't 3 times better. This was a gulf so vast that comparing them felt almost unfair. The numbers don't lie. When you calculate the statistical likelihood of our standard model being correct, the one that assumes uniform matter distribution, you get a result equivalent to flipping a coin and getting heads 13 times in a row. Possible, but so improbable that any reasonable person would start questioning the coin. The void model? Its probability is like flipping heads twice in a row. Completely mundane. Exactly what you'd expect. Here's how it works, and it's surprisingly elegant. Imagine the universe as a vast cosmic web, a 3-dimensional structure of galaxy clusters connected by filaments with enormous voids in between. We've known about these voids for decades, but what if we lived in one? Not just any void, but a particularly large one. Inside this underdense region, gravity pulls in a specific direction. All that missing matter, all those galaxies that aren't here, creates a gravitational gradient. The dense material outside the void tugs at everything within it. This creates what astronomers call bulk flows. Galaxies don't just recede from us because space is expanding. They also drift outward, away from the void's center, drawn by the gravity of the denser universe beyond. Now here's where it gets interesting. When astronomers measure a galaxy's light, they observe something called redshift, the stretching of light waves as the galaxy moves away. They assume all of this motion comes from cosmic expansion. But if the galaxy has an extra velocity from being pushed outward by this gravitational gradient, its redshift appears slightly larger than it should. The light is redshifted more. The galaxy appears farther away than it really is. The baryon acoustic oscillations, those ancient sound waves we use as cosmic rulers, seem stretched across a larger distance. The measurements inflate. The data points rise above predictions, and suddenly, an anomaly that looked like a fundamental failure of our model becomes something much simpler. Evidence of where we actually are. The researchers tested 3 different mathematical profiles for this void. They tried a Maxwell-Boltzmann distribution, a Gaussian curve, an exponential decline. All three worked. All three improved the fit dramatically, but the Gaussian profile fit best of all. The statistical measure, chi-squared, the standard tool cosmologists use to judge how well theory matches observation, dropped from 75.7 in the standard model to between 47 and 51 in the void models. That's a reduction in tension from 3.3 sigma to between 1.1 and 1.4 sigma. 3.3 sigma means the standard model is seriously, probably wrong. 1 sigma means the void model is just normal, boring even. The really stunning part, when you look at more distant galaxies billions of light years away, the void's influence diminishes. At those vast distances, the measurements snap back into alignment with predictions from the cosmic microwave background, that ancient light from the Big Bang itself. The void can't reach that far. Its gravity fades with distance, so the universe tells a coherent story. Nearby, we see the effects of living in a local void. Distantly, the universe behaves exactly as our models predict. The transition between these two regimes happens exactly where the mathematics says it should. This changes everything. Or perhaps it changes nothing, because here's the uncomfortable truth. We might not live in a special place in any meaningful sense. We're not at the center of creation. We're just here, in a region that happens to be slightly less dense than average, statistically unremarkable, cosmologically ordinary, but locally consequential to our measurements. It's the cosmic equivalent of taking a photograph of a forest and then realizing you're standing in a clearing. The forest is still a forest. Your clearing doesn't make it less of a forest, but it absolutely matters for understanding what you see from where you're standing. The 2025 analysis, published in the monthly notices of the Royal Astronomical Society, represents more than just a technical recalibration of our data. It's a reminder of something fundamental about science itself. We build models. They work brilliantly. Then, sometimes, they fail in just the right way to reveal something we never expected. Not a failure of the universe, but a failure of our assumptions about our place within it. We assumed the universe was uniform around us. The data suggested otherwise. Sometimes the measurements aren't wrong. Sometimes we're just standing somewhere unexpected. And that's not a problem to be solved. It's a mystery waiting to be understood. The grand cosmic drainage. Our universe hides a secret in its geometry. Statisticians can describe it with numbers, but numbers alone miss the poetry. The true story emerges when we watch galaxies themselves, billions of them, all moving in concert, all dancing to the same invisible rhythm. Here's what we're seeing. Galaxies trapped inside cosmic voids don't behave like their neighbors in denser regions. They move differently. They flee. And we're fleeing too. Right now, the Milky Way is hurtling away from the center of a colossal void at 600,000 miles per hour. Not because some force is pushing us from behind. No, because an immense, invisible boundary lies between us and emptiness, and everything beyond that boundary is pulling us outward with relentless gravity. Matter on the rim of the void, vast filaments and superclusters, acts like a cosmic drain, sucking everything toward them, away from the hollow interior. Astronomers call this phenomenon bulk flow. To measure it, they do something elegantly simple. Pick thousands of galaxies scattered across an enormous sphere. Measure how fast each one is moving, and calculate the average. The result? A motion so coordinated, so vast in scale, that it shouldn't exist according to our standard models of the universe. In 2023, the latest Cosmic Flows catalog revealed something troubling. The bulk flow doesn't weaken as expected. It doesn't average out. It strengthens. The deeper astronomers look into space, the more they measure these coordinated motions. The observed flow reaches speeds 4 times higher than theory predicts. This is the universe saying our models are incomplete. But then something remarkable happened. In 2024, physicists Sergei Mazurenko and colleagues ran the numbers on void models. Universes shaped by these cosmic hollows. The void models predicted exactly what we observe. They predicted the bulk flows. They predicted the strength. They predicted the pattern. And suddenly, the picture crystallized. Imagine standing inside an enormous bowl made of invisible matter. Imagine that bowl is mostly empty, a void, while its rim and everything beyond gleams with galaxies and dark matter. Everything inside that bowl wants to escape it. Not because of a push, but because gravity from the dense rim continuously pulls. The motion is coherent. The flow is unified. A river flowing from emptiness towards substance. The KBC void, the immense hollow that houses our own cosmic neighborhood, measures roughly 1 billion light-years across. Inside it, galaxies stream outward in all directions. Their speeds depend on distance from the void's center. At the core, they accelerate away at maximum velocity. Farther out, the flow slows. Eventually, at the void's boundary, the expansion returns to the cosmic average, but we don't sit at the void's center. We occupy something far more intricate, a thin, flattened sheet of galaxies called the local sheet, and this sheet borders an even smaller void, a cavity within the cavity, extending about 200 million light-years. We're positioned at its edge, watching it drain. Galaxies in our local neighborhood flee from this emptiness at 160 miles per second. The effect resembles water circling a drain, pulled by invisible geometry. This is the cosmic web's true nature. Matter doesn't distribute randomly. It flows out of voids and accumulates along their boundaries, creating the filaments and sheets we see, a vast architecture built by gravity itself. We live inside this drainage system, watching it work in real time. But there's more to this story. These forces didn't just begin yesterday. They've been sculpting the cosmos since the very beginning. Rewind 13 billion years. The first stars ignite in the primordial darkness. The universe is a newborn, barely 1/10 of its current age, and yet something impossible already exists. Supermassive black holes. Not small ones, not even large ones. Monsters weighing more than 1 billion suns each. The James Webb Space Telescope found them, and they weren't unique. Several quasars, studied by the ASPIRE program, blazed across the early universe, so luminous they outshone their entire galaxies. One of them, J0305-3150, emerged just 830 million years after the Big Bang. Already ancient by infant cosmic standards, already hungry, already powerful. The universe was younger then, denser, wilder, but even then, the forces we see today were already at work, reshaping reality, pulling matter together, carving hollows in the fabric of space itself. In the depths of the early universe, we've discovered something that shouldn't exist. Astronomers found massive black holes, billions of times heavier than our sun, lurking in the cosmic dawn. Objects so ancient, so impossibly huge, that they shatter everything we thought we knew about how the universe builds its monsters. Here's the problem. Black holes grow by eating. They pull in matter, tear it apart, heat it to incomprehensible temperatures, and that superheated material radiates energy outward like a cosmic furnace. This radiation pushes back against the infalling material. It's a natural brake on growth. Even under perfect conditions, even when a black hole is gorging itself as fast as physics allows, it can only double its mass once every 50 million years. Now do the math in reverse. We see a black hole with 1 billion times the Sun's mass. It existed just 800 million years after the Big Bang, starting from the seed black holes that collapse from early stars, mere hundreds of times the Sun's mass. Reaching 1 billion solar masses requires doubling your weight 20 times. 20 doublings at maximum speed demands over 1 billion years. But the universe is only 800 million years old in this scenario. The timeline doesn't fit. It can't fit. Something is wrong. Either these black holes started impossibly large, or they grew through mechanisms we haven't yet discovered. The first possibility: direct collapse black holes. In the turbulent infancy of the universe, perhaps massive clouds of primordial hydrogen could collapse directly into black holes without pausing to form stars first. No stellar intermediary, just raw ancient gas collapsing straight into the abyss. This process could birth black hole seeds, thousands or even millions of times the Sun's mass. A colossal head start. The second possibility: super Eddington accretion. Black holes consuming matter faster than radiation pressure should permit. Somehow, they're cheating the cosmic speed limit on feeding. Both remain theoretical. Neither has been caught red-handed. Then came new evidence. Roberto Maiolino's team pointed the James Webb Space Telescope at these impossible ancient quasars and saw something remarkable. Extremely dense gas swirling in their cores. Signs of material being devoured at ferocious rates. But they also saw something stranger. Powerful winds. Matter ejected at tremendous velocities, screaming away from the black hole itself. Here's the violence. Material falling in while material blasts out. These early quasars aren't elegant, stable feeders. They're desperate, chaotic, consuming whatever fuel exists in their sparse cosmic neighborhoods in violent, rapid bursts. A cosmic feeding frenzy unlike anything we see in the universe today. And then, these objects apparently vanished into silence. Some scientists propose a stunning idea. These black hole-infested regions, transformed into the voids we see scattered across the modern universe. Ancient overdensities that allowed rapid black hole growth, followed by expansion, followed by matter evacuation, leaving behind the ghost-like voids we detect today. But to test this idea, we need to understand how voids themselves form. They're not true vacuums. That's a common misconception. The voids we map contain galaxies, stars, dark matter, ordinary matter. The term void describes relative density, not absolute emptiness. It's about poverty, not absence. Yet our neighborhood, the KBC void containing our own Milky Way, carries a profound deficit. Matter concentration here measures roughly 80% of the cosmic average. Some measurements suggest it dips even lower, to 50%. The exact number depends on how far observations reach beyond the void's edge and how scientists normalize the data. But this much is certain. We live in an underdense region. We have 20% fewer atoms than a typical cosmic neighborhood. This seemingly small shortage creates consequences that ripple across the universe. Gravity weakens where matter thins. With less mass pulling inward, the expansion of space encounters less resistance. Imagine a balloon inflating inside a room. In one corner, heavy weights hang from strings attached to the balloon surface, pulling it back. In another corner, lightweight strings barely tug. The balloon stretches faster where resistance is weakest. The universe does the same. Regions with below-average matter density expand slightly faster than average. Regions with above-average density expand slightly slower. And we live in a region that's expanding faster than the cosmic norm. For billions of years, we never noticed. The universe's greatest illusion. Imagine you're standing in a vast, empty valley at night. Around you, the darkness stretches endlessly. But in one direction, You see lights. A distant city glowing on the horizon. You measure how fast that city is moving away from you. The numbers seem clear, straightforward. Then you climb a mountain and look down. You realize you weren't standing on flat ground at all. You were in a depression, a massive sinkhole carved into the landscape. And that city? It's not as distant as you thought. It's not moving as fast as you calculated. Everything changes when you understand where you actually are. This is our cosmic reality, and it took us decades to figure it out. For years, astronomers have measured how fast the universe is expanding. Two methods, two different answers. Scientists using nearby galaxies, measuring the light from exploding stars and pulsing stars called Cepheids, got one number. The cosmic microwave background, that ancient light from the universe's birth, suggested something else. Both were right. Both were wrong. Until they realized the truth, we live inside a cosmic void. Not just any void, the KBC void. A region of space so empty, so underdense that it warps everything we see. When you measure the universe from inside a hole, you're not measuring the universe, you're measuring the hole. Here's what's happening. All around us, across billions of light years, matter clusters and clumps under gravity's relentless pull, galaxies bunch together. They form filaments, cosmic highways where billions of galaxies stream together. And between these structures, nothing. Enormous voids, empty regions stretching across 500 million light years or more. Our universe is less like a uniform foam and more like Swiss cheese, mostly whole. We live in one of those holes, and it changes everything. When you're trapped in an underdense region, your measurements become systematically biased. When we calculate the universe's expansion rate using local galaxies, using supernovae exploding nearby, we're sampling an environment that's expanding faster than average. Why? Because there's less gravity here, less matter, less stuff pulling everything inward. So space expands more aggressively. We measure this accelerated local expansion and assume it represents the whole universe. It doesn't. We're measuring a symptom of our underdense neighborhood, not the cosmic truth. The cosmic microwave background sees the big picture. That ancient light traveled through the entire universe before reaching us. It averages out all the voids and filaments, all the clumps and empty spaces. It reveals the universe's true expansion rate, the global average. Local measurements reveal only what's happening here, in our peculiar cosmic backyard. Both measurements are accurate. They're just measuring different things. Computer simulations prove this isn't speculation. Scientists start with initial conditions matching the cosmic microwave background observations. The universe, as it was 380,000 years after the Big Bang. They let gravity do its work. They watch the universe evolve forward using only known physics, no tricks, no adjustments. And what emerges? Voids. Enormous voids, just like ours. The simulations show voids should occupy roughly 70% of the universe's volume. Yet they contain barely any galaxies at all. They're cosmic emptiness. Multiple lines of evidence converge on this reality. Distant quasars, brilliant objects powered by supermassive black holes billions of light years away, get lensed by gravity. The universe's massive structures bend light like a lens, distorting the quasar's appearance. The strength of this lensing reveals the total mass along the line of sight. Some sight lines show weaker lensing than expected. Why? They're passing through underdense regions, voids. The pattern matches perfectly with what large-scale surveys predict. We can see the universe's scaffolding of voids and filaments written in light. Now, here's where it gets strange. A supercluster lives inside our void, the Laniakea supercluster. Its name means immeasurable heaven in Hawaiian. and it contains roughly 100,000 galaxies stretching across 500 million light-years. Our Milky Way occupies one tiny corner of this structure. The Virgo supercluster lives here, the Hydra Centaurus supercluster, the Pavo Indus filament, all of them. One unified structure discovered by astronomer Brent Tully and colleagues in 2014. This discovery seemed to answer a fundamental question. What defines our cosmic neighborhood? Laniakea seemed like the answer. A massive concentration of galaxies, a dominant feature of the universe. Then came the realization that rewrote our understanding. Laniakea sits inside the KBC void. The entire supercluster, all those galaxies, all that matter, exists within an overall underdense region. A paradox seemed to emerge. How can you have a massive concentration of galaxies inside a void? Scale is the answer. Context is everything. Think of it this way. A mountaintop is a peak, but a mountaintop in a valley remains lower than a mountaintop in an adjacent mountain range. Laniakea is the densest region within a larger underdensity. It rises above its surroundings locally, but remains lower than the truly dense structures beyond the void's edge. The void doesn't eliminate local structure. It suppresses the average density across enormous volumes. The gravitational dynamics reveal this layered reality. Galaxies stream toward the Great Attractor, a concentration of mass near Laniakea's center. But simultaneously, the entire supercluster participates in an outflow away from the KBC void's center. These motions combine. Our galaxy, the Milky Way, moves toward the Shapley concentration, a massive cluster of galaxies beyond Laniakea's edge. We also move away from the dipole repeller, an underdense region on the opposite side of the sky. The repeller doesn't push. It simply fails to pull as strongly as surrounding matter. It's not a force. It's an absence of force. We are not special in living near a void. Many civilizations, if they existed, would live within voids. But we are special in how remarkably large our void is, and in how profoundly it distorts our perception of cosmic truth. We built telescopes to understand the universe. Those telescopes revealed we had been looking at the universe through a cosmic lens, one that magnifies, warps, and systematically biases everything we see. And yet, this discovery is triumphant. Science works. We made conflicting measurements. We didn't ignore the conflict. We asked deeper questions. We built simulations. We tested predictions. We gathered evidence. And the universe revealed its secret. We live in darkness, but measuring darkness requires understanding what fills the bright spaces in between. Picture this. We are not standing still in the universe. Right now, the Milky Way is rushing through space at 160 miles per second, fleeing something. That something is nothing. We are running from a void. This discovery upends everything we thought we knew about superclusters. Those vast cosmic cities housing billions of galaxies. Scientists once believed these structures were stable, permanent fixtures of the universe, held together by their own gravity like cosmic fortresses. But recent analysis reveals the truth is far stranger. The void surrounding us is so powerful, so relentless in its expansion, that it may be tearing apart the very fabric of the supercluster itself. Laniakea, the supercluster we call home, might not survive the cosmic ages. It's not gravitationally bound. The void's outward push is stronger than the inward pull of gravity. As the void continues to expand, the galaxies that appear grouped together today will scatter like refugees, fleeing an encroaching darkness. Superclusters aren't permanent structures. They're temporary gatherings, cosmic traffic jams that will eventually dissolve into the void. And there's more. The void doesn't just push galaxies around. It rewrites their very nature. Galaxies living in voids are systematically different from their cousins in denser regions. They're smaller, they're bluer, they're younger. And here's the paradox. Despite having less gas to work with, they form stars more actively, more frantically, like they're racing against time. Why? The answer lies in geography. In crowded regions of space, galaxies collide constantly. These violent encounters are cosmic catastrophes. They heat gas to millions of degrees, blast it into space, and shut down star formation completely. It's like smashing a factory to pieces. But in voids, galaxies drift alone. They evolve in isolation, holding onto their gas reserves, steadily forging new stars, generation after generation. The Milky Way's own history, how it became what it is, was shaped by this lonely neighborhood. We grew differently because we live differently. But where did voids come from? The answer takes us back to the beginning of time itself. In the first moments after the Big Bang, space was almost perfectly smooth, nearly uniform, almost boring, but quantum mechanics wouldn't allow that perfection. At the smallest scales, uncertainty reigned. Cosmic inflation, the universe's violent expansion in the first fraction of a second, amplified those quantum whispers into macroscopic variations, tiny density ripples. One region slightly more dense than another by just 1 part in 100,000. These microscopic differences? They contained the blueprints for everything. Gravity seized on these variations like a sculptor discovering stone. Dense regions pulled in more matter, becoming denser still. Underdense regions lost matter to their surroundings, becoming emptier. The process fed on itself. Differences that began impossibly small became cosmic abysses. For the first few 100 million years, the universe remained relatively uniform. The expansion hadn't yet stretched space far enough for gravity to carve extreme contrasts. Voids existed, but they were shallow, barely noticeable. Then galaxies ignited. They were born in the densest regions, clustering together, wielding enormous gravity. These massive concentrations acted like cosmic vacuum cleaners, sucking matter from their surroundings even faster. Voids deepened, they expanded. The contrast between crowded and empty became stark. Then, about 6 billion years ago, everything changed. Before that moment, matter ruled the cosmos. Gravity dominated every calculation, every force, every outcome. Expansion slowed everywhere, though it slowed less in voids than in dense regions. But then dark energy awakened, the mysterious force that comprises 68% of the universe. And the rules of the game flipped entirely. Expansion stopped slowing. It started accelerating. In dense regions, local gravity could partially push back, creating pockets of resistance. But in underdense regions, in voids, dark energy faced almost no opposition. It accelerated expansion with unopposed fury. The voids began inflating faster than normal cosmic expansion alone could explain. Their boundaries rushed outward like shock waves, forcing their way into surrounding space. The local void, the one we live next to, stretches roughly 200 million light-years across, and it's pushing us, pushing the Milky Way, pushing everything nearby at 160 miles per second. That's faster than cosmic expansion alone would produce at this distance. That extra velocity? It comes from repulsion, a gravitational push away from emptiness itself. Here's the truly unsettling part. In an underdense region, matter experiences a net force pointing away from the center, as if invisible hands were shoving it outward. Negative pressure gradients. The void doesn't pull, it repels. Space itself between us and nothing is structured in a way that forces us apart. We are not drifting randomly through the cosmos. We are being expelled. The universe's greatest secret, where almost nothing lives. Imagine the universe as a frozen foam, dense walls, empty bubbles. Where those walls crash together, thick strands form. Where the strands intersect, massive knots accumulate. This is the cosmic web, and it's one of the most mind-bending structures we've ever discovered. But here's the thing. We live inside a bubble. A massive, almost impossibly empty bubble. Matter doesn't actively blow these bubbles outward. Instead, galaxies simply fall. They tumble toward denser regions, toward the walls and filaments where gravity is strongest. As they migrate, they leave behind increasingly sparse regions. The emptier spaces grow larger. The walls get thicker. The bubbles expand. Not because something pushes them, but because everything around them is being pulled away. Computer simulations? Watching this process unfold in cosmic time reveals something striking. Voids grow primarily through evacuation. Matter drains out. It's like watching a stadium empty after the final game. Except the stadium is a region of space billions of light years across, and the evacuation takes billions of years. Eventually, voids reach an equilibrium. Gravity wants to pull everything inward. Cosmic expansion wants to push everything outward. When these forces balance, the void stops growing. It settles at a characteristic size. The largest typical voids in the universe span several 100 million light years. But we don't live in a typical void. We live in the KBC void. It's 2 billion light years across. That's roughly 5 to 10 times larger than it should be. Some of the finest cosmologists in the world look at this and simply ask, how is this possible? Standard models of cosmology struggle to explain it. According to the conventional story of structure formation, extreme supervoids this massive shouldn't exist yet. The universe isn't old enough. There hasn't been enough time for gravity to carve out such enormous empty regions. Some researchers propose alternative theories, modified gravity models that allow structure to form faster, creating these cosmic anomalies. But the debate rages on. Whatever mechanism built our void, the consequences are profound. The cosmic web is breathtaking in scale. Imagine the universe organized like biological tissue, or better yet, like a neural network frozen in space. The densest components are the galaxy clusters, massive knots where filaments intersect, containing thousands of galaxies bound together by gravity. The strands connecting them are the filaments themselves, highways of galaxies stretching across unimaginable distances. Individual filaments can stretch for 300 million light years or more. The Sloan Great Wall, discovered in 2003, measures 1.4 billion light years long. The Hercules Corona Borealis Great Wall may span 10 billion light years, though astronomers still debate whether it's truly a single connected structure or several alignment coincidences. These filaments aren't solid objects. They're not like ropes made of matter. Instead, they're highways. Galaxy clusters and groups dot the path, connected by diffuse strands of gas and dark matter. Matter concentrates along these routes like cities along ancient trade routes. Galaxies don't sit still. They flow. They fall along the filaments toward the massive clusters, accelerating under gravity's relentless pull. Where filaments intersect, walls emerge. Vast two-dimensional sheets of galaxies, typically 100 to 300 million light years across, but only 10 to 30 million light years thick. These walls separate adjacent voids, like the panels of a foam structure. Our own galaxy, the Milky Way, sits in such a wall, a flattened cosmic sheet that contains Andromeda and hundreds of other galaxies spread across a two-dimensional distribution. Most galaxies in the universe actually live in walls and filaments. not in the massive clusters, not in the voids. They populate these intermediate density environments where steady star formation unfolds. These are the typical galactic habitats, the places where life is possible. But the voids are something else entirely. They comprise roughly 70% of the universe's volume. 7 out of every 10 parts of space are essentially empty. Yet despite occupying most of the universe, voids contain only a small fraction of galaxies. Typical voids span 30 to 100 million light-years. The Bode's void, discovered in 1981, stretches 330 million light-years and contains only about 60 galaxies. For comparison, take that same volume and place it in average cosmic space. You'd find roughly 2,000 galaxies. That emptiness is profound. Not absolute, never absolute, but profound. A cosmic loneliness that echoes across the darkness, yet even these measurements may be incomplete. Recent surveys reveal even larger structures hiding in our data. Baryon acoustic oscillations create periodic clustering patterns on scales approaching 490 million light-years. The sound horizon, an echo from the early universe's acoustic waves. Some of these apparent structures might not be real at all. They could be statistical fluctuations. Patterns our pattern-seeking minds impose on randomness. The debate continues about what constitutes a genuinely connected structure versus multiple features that simply align in our line of sight. But this much remains undisputed. The universe is organized on scales so vast and complex that our minds struggle to grasp it. Walls, filaments, clusters, voids. And within one of those voids, one of the most extraordinarily empty regions ever discovered, lives everything we've ever known. The universe's hidden contradiction. Gravity doesn't just pull on things. It sculpts reality itself. It carves space into a vast network of walls and voids, density and emptiness, light and shadow. We live in one tiny bubble within this cosmic foam, and that bubble, our peculiar location in space, holds a secret that threatens everything we think we know about the universe's history. Here's the problem. We can measure how fast the universe is expanding. This expansion rate, called the Hubble constant, is absolutely crucial. Because if you know how fast the universe is expanding now, you can rewind the clock. You can calculate how old everything is. And that's where things get weird. Different methods give us different answers. When astronomers measure expansion locally, using nearby galaxies and supernovae, they get a surprisingly fast rate. According to these measurements, the universe reached its current size in only about 12.5 billion years. But here's the catastrophic problem. We have found stars that are older than that. In the hearts of globular clusters, scattered throughout our galaxy, live some of the universe's most ancient stars. We can determine their age by studying their light. We understand how stars burn fuel. We know that a star's mass, its composition, and how hot its surface is all tell us exactly how old it must be. The physics is bulletproof. The calculations are sound. And the oldest globular cluster stars? They're over 13 billion years old. Think about that. The universe itself would be younger than the stars inside it. That's like saying a child is older than their mother. It's logically impossible. This is the Hubble tension. And it's not a small discrepancy we can chalk up to measurement error. Something fundamental is broken in our understanding. So what do we do? One answer comes from something called the void hypothesis. Imagine the universe isn't uniform. Imagine we live inside a massive underdense region, a cosmic bubble where there's less matter than average. In this void, space itself expands faster than it does elsewhere in the universe. Our local measurements see this enhanced expansion. But that's not the true expansion rate of the entire cosmos. If this is correct, everything suddenly clicks into place. The universe is still 13.8 billion years old. The stars are still younger than that. And we stop measuring an impossible universe. Our local expansion rate tells us about our neighborhood, not the whole cosmos. It's like measuring the temperature in a hot room and concluding the entire planet must be on fire. The elegance of this solution is seductive. It preserves everything we know. The cosmic microwave background, that ancient light from the Big Bang, remains exactly as we understand it. The abundance of light elements formed in the early universe still matches our predictions. The large-scale structure of galaxies and clusters still makes sense. We're not inventing new particles. We're not rewriting fundamental physics. We're just recognizing that we live in an unusual place. But elegance isn't truth. Some physicists think the real problem runs deeper. They're asking a dangerous question. What if gravity itself is wrong? General relativity has dominated for over a century. It predicted Mercury's orbit perfectly. It told us gravitational waves existed before we ever detected them. Einstein's theory works everywhere we've tested it. And yet, we've had to invent dark matter to explain why galaxies spin too fast. We've had to invent dark energy to explain why the universe is accelerating. 95% of the universe is now made of things we cannot see and do not understand. Maybe we're building an elaborate fiction to prop up a broken foundation. In 1983, physicist Mordecai Milgram proposed something radical: modified Newtonian dynamics, a change to how gravity itself behaves. In the ultra-weak gravitational environments found in the outer regions of galaxies, gravity doesn't fade away as quickly as Newton or Einstein said it should. It stays stronger. Suddenly, galaxies spin exactly as fast as they do. No dark matter needed. The mystery dissolves, and the theory makes testable predictions. Predictions that, in many cases, match what we actually observe. We stand at a crossroads. One path leads through voids in cosmic geography. The other questions the laws of physics themselves. The universe is telling us something is wrong. We just don't know what yet. The universe's greatest mystery might be hiding in plain sight. Imagine waking up and discovering your entire neighborhood is a statistical impossibility. That's where astronomy stands today. We live inside something that shouldn't exist, a cosmic void so enormous, so improbable, that it forces us to ask one of the deepest questions in physics. Is gravity itself broken? Number, the problem that rewrites physics. For decades, cosmologists believed gravity worked the same everywhere, governed by Einstein's equations. But those equations have a problem. They predict that a void like the one we inhabit, a region of space spanning 2 billion light-years with far fewer galaxies than the rest of the universe, should appear spontaneously less than 1% of the time. Less than 1%. Yet here we are. When scientists realized this, they faced an uncomfortable truth. Either the universe is far stranger than we thought, or something fundamental about how gravity works remains hidden from us. Enter Pavel Krupa and a bold new framework. Instead of accepting Einstein's gravity as gospel, Krupa's team asked a radical question. What if we're wrong about how gravity behaves on the largest scales? Nurture a new kind of universe. They built a hybrid model called NUHDM, that combines modified gravity with an exotic ingredient, sterile neutrinos. These are ghostly particles with barely any mass, about 11 electron volts of rest energy. They slip through ordinary matter almost unnoticed, yet they shape how the cosmos evolved. Here's where it gets fascinating. This modified framework doesn't just explain the cosmic microwave background radiation, the ancient light from the universe's infancy. It does something standard gravity cannot. It allows voids to grow faster, deeper, and earlier than Einstein's equations permit. In 2020, Indra Nilbanek and colleagues ran simulations using this modified force law. Starting from the conditions present, moments after the Big Bang, they let the universe evolve forward, and something remarkable happened. The voids grew, faster than they should, deeper than they should. And when the simulations finished, the result matched our cosmic surveys perfectly. The structure they created looked exactly like the void we observe around us. In standard cosmology, this should have been impossible. The case against modified gravity. But wait, before we declare gravity fundamentally broken, we have to confront an uncomfortable fact. Modified gravity theories have their own problems. When light bends around massive clusters of galaxies, a phenomenon called gravitational lensing, observations show the light bends more sharply than modified gravity predicts. The Bullet Cluster, where two galaxy clusters violently collided billions of years ago, reveals an even more troubling discrepancy. The gravitational effects don't align with visible matter. They align with dark matter. The invisible stuff that Einstein's gravity demands must exist. Proponents of modified gravity argue these systems simply require additional physics. Critics counter that adding patches to a theory is no different than what defenders of dark matter do. Both sides agree on one thing, though. Something fundamental remains hidden. Either the universe contains exotic forms of matter we've barely glimpsed, or gravity itself operates by rules we don't yet understand. The ultimate measurement problem. But here lies perhaps the deepest irony of all. We cannot step outside the universe and look back at ourselves. Every observation, every measurement, every telescope pointed skyward originates from within the structure we're trying to study. We are prisoners, trying to measure the size of our cell from inside it. This creates a profound blind spot. To determine if we live in an underdense region, astronomers must compare local galaxy density to the cosmic average. But measuring the cosmic average requires surveying vast distances. And here's the trap. Surveys that originate from inside an underdense void initially sample mostly that very void. You can't recognize you're standing in a hole until you climb far enough out to see the rim. For decades, early surveys simply didn't go deep enough. The Harvard Center for Astrophysics Redshift Survey in the 1980s mapped galaxies out to a few 100 million light-years. Remarkable work. It revealed the cosmic web for the first time, the intricate patterns of clusters and filaments where galaxies congregate. It showed that the universe is not uniform, but it couldn't see the void. A structure spanning 2 billion light-years demands observations reaching well beyond its boundary. Surveys limited to a few 100 million light-years are like trying to photograph the Earth while standing in your living room. The breakthrough. Then came near-infrared light. The 2-micron all-sky survey, 2MASS, changed everything. By observing at wavelengths where dust barely obscures the view, astronomers could penetrate cosmic regions where optical telescopes failed. The follow-up redshift survey measured distances to over 43,000 galaxies, extending knowledge to roughly 380 million light-years. In 2013, Keenan, Barger, and Cowie analyzed the data. What they found was unmistakable. Galaxy density increased systematically with distance from Earth. The farther out they looked, the more galaxies they found. We aren't at the center of the universe. We're at the center of an underdensity, a void. The KBC void had been discovered, not through exotic physics or revolutionary instrumentation, but through a simple, profound observation. We live in a cosmic desert, and that void might just hold the key to rewriting everything we thought we knew about gravity itself. The universe's greatest mystery was hidden inside our own backyard. Scientists were skeptical. Could this be a mistake? A trick of the data? An illusion created by how they were looking? But then something remarkable happened. Team after team, using completely different data sets, kept finding the same thing. Observations from optical telescopes, X-ray observations from space, radio signals from distant galaxies. Every single wavelength told the same story. The Sloan Digital Sky Survey, which mapped millions of galaxies across vast swaths of the sky, confirmed it again. By 2017, the scientific community had no choice but to accept the truth. We live in a cosmic void. Our corner of the universe is genuinely emptier than it should be. But here's the cruel irony. The void was hiding in plain sight the entire time, not because of anything special about the void itself, but because it's nearly impossible to recognize how unusual your own location is when you have nowhere else to stand and observe from. It's like asking a fish to describe what water is like, yet this void didn't just appear out of nowhere. Its story begins at the very dawn of creation itself. 1/1,000,000th of a trillionth of a trillionth of a second after the Big Bang, something extraordinary happened. The universe was violently inflating, expanding at speeds that make light look like it's standing still. And rippling through this expanding cosmos were quantum fluctuations, tiny vibrations in the very fabric of reality itself, born from fundamental uncertainty, written into the laws of physics. These microscopic wobbles in energy density were stretched by inflation like taffy being pulled apart. What started impossibly small became impossibly vast. By the time inflation stopped, those quantum whispers had grown to span millions of light years. These frozen patterns became the blueprint for everything that came next. The Planck satellite captured this story with extraordinary precision. It mapped the entire sky and measured the temperature of ancient light, the cosmic microwave background, to millionths of a degree accuracy. Hotspots revealed where the early universe was slightly denser. Cold spots showed where it was slightly less dense. And when physicists compared what they saw to predictions from quantum theory, the match was almost perfect. This stands as one of the greatest triumphs in all of physics. A theory conceived decades ago, now verified across the entire observable universe. But maps are just the beginning. What happened next was gravity. From these tiny variations in density, gravity became a sculptor. It pulled on matter in the overdense regions, making them even denser. As material flowed inward, the process accelerated. A small enhancement became a larger one. Larger enhancements became proto-galaxies. Proto-galaxies merged into galaxies. Galaxies gathered into clusters. Clusters connected along threads of matter called filaments, and filaments outlined vast empty spaces, voids. The entire cosmic web, everything we see when we peer into the universe, emerged from the amplification of quantum noise, stretched to astronomical scales. But underdense regions followed the opposite fate. A region that started even slightly below average density lost material to its surroundings. As matter drained away, it became even emptier. The process fed on itself. Over billions of years, what began as a shallow depression deepened into an abyss. The largest voids in the universe today, the supervoids, trace their lineage back to the rarest, most extreme underdensities in the primordial quantum fluctuation field. Billion-year-old gravitational avalanches. And here's where it gets personal. The void we live in exists because long ago, an unusually large underdensity in the quantum fluctuation field happened to overlap with our location. Statistically, in a universe large enough, such extreme features must exist somewhere. The question scientists grapple with now is not whether they exist, but whether our presence in one is genuinely remarkable or simply inevitable. Yet this discovery harbors a deeper secret. Our void might hold the key to one of cosmology's greatest unsolved mysteries, the Hubble tension. For years, different ways of measuring the universe's expansion rate gave conflicting answers. As measurements grew more precise, the conflict only deepened. Then a possibility emerged. What if we're not seeing reality clearly because we're trapped in an underdense bubble? What if the void is distorting our view of the cosmos itself? The universe, it turns out, had been trying to tell us something all along. We just needed to look in the right place. Our own backyard. The cosmic mystery. Hiding in empty space. There's something profoundly strange about the universe we inhabit. It's not just vast, it's unimaginably, almost aggressively empty. And hidden inside this emptiness lies one of science's greatest unsolved mysteries. Look out at the cosmos, and you'll see galaxies arranged in a cosmic web. They form filaments and clusters, connected by threads of matter stretching across billions of light years. But between these structures, almost nothing. Voids. Regions so empty that they dwarf anything we can comprehend on Earth. Our galaxy, the Milky Way, doesn't live in some crowded galactic metropolis. We live in one of these voids, a region of space so underpopulated that it shapes everything about us. For decades, astronomers thought they understood the universe's basic blueprint. Galaxies cluster, matter attracts, gravity rules. Then, in 1998, everything changed. Two teams of astronomers made an observation that shattered our understanding of reality itself. The universe wasn't just expanding, it was accelerating, speeding up, as if invisible hands were pushing galaxies apart, faster and faster, fighting against gravity itself. They called it dark energy. And here's the staggering part. It makes up 68% of the entire universe. Think about that. Nearly 70% of all energy in existence is something we can't see, can't touch, and barely understand. It's not matter. Matter attracts. Gravity pulls things together. Dark energy does the opposite. It pushes. It accelerates expansion. It's as if the universe has a foot pressing down on the gas pedal, and we have no idea who's driving. The current theory treats dark energy like a cosmic constant. Uniform, unchanging, the same everywhere and everywhen. It's an elegant idea. Simple, and it explains most of what we observe. But there's a problem. Recent observations from the Dark Energy Spectroscopic Instrument hint at something more complex. Maybe dark energy isn't constant. Maybe it changes over time. Maybe it varies from place to place. If that's true, we need to completely rethink cosmology. Now, here's where voids become crucial. These vast, empty regions are where dark energy's true nature reveals itself. In dense clusters of galaxies, gravity is ferocious. Matter packs together, and gravitational attraction dominates. Dark energy barely whispers. But in voids, here, matter is scarce. Gravity is weak, and dark energy can strut its stuff without interference. This is where the story gets really interesting. Voids don't expand uniformly. In their centers, where dark energy faces no gravitational resistance, space stretches faster than in the dense regions surrounding them. This differential expansion creates an illusion. It looks like voids are actively pushing galaxies away, but they're not. There's no repulsive force. Instead, dark energy simply accelerates expansion more freely, where gravity isn't holding it back. It's like watching water flow downhill, but the hill is made of gravity, and the water is space itself. This has profound consequences for how galaxies evolve. A galaxy born in a void lives a fundamentally different life than one born in a crowded cluster. In dense regions, galaxies collide. They merge. Close encounters strip away gas. Violent interactions trigger cosmic fireworks of star formation. These galaxies get battered, torn apart, transformed. Many eventually become passive, old elliptical forms, dead galaxies containing mostly ancient stars. But void galaxies, they evolve in peace. They avoid the cosmic harassment. With few neighbors, they keep their gas intact. They continue forming stars. They remain spiral galaxies, dynamic, young, alive. And that's exactly what we observe. The Milky Way and Andromeda, our closest galactic neighbor, are both spiral galaxies, rich in gas and young stars. We didn't randomly end up in this void. Our galaxy's very nature, the fact that it's a spiral, the fact that it's still birthing stars, stems from our location in one of the universe's emptiest places. We evolved inside a cosmic sanctuary, and we owe it all to dark energy. Scientists now realize voids are natural laboratories. They're where dark energy's influence is starkest, least contaminated by gravitational noise. By measuring how voids expand across cosmic time, by watching how their shapes change as the universe ages, we can test whether dark energy really is constant or whether it's something far stranger. This is what future surveys will explore, measuring voids across billions of years of cosmic history, charting how their properties shift, testing whether dark energy behaves as current theory predicts, or whether it reveals a deeper secret about reality. The mystery remains open. Dark energy could be Einstein's cosmological constant, a fundamental property of space-time itself. It could be a dynamic field, something that evolves and changes. It could signal a fundamental modification to gravity at cosmic scales, or it could be something we haven't imagined yet. What we know for certain is this: the universe is mostly empty. That emptiness is driven by something we don't understand. And the very fact that we exist, that our galaxy evolved the way it did, that life emerged on a spiral world in an underdense void, all of it depends on this invisible force reshaping the cosmos around us. The cosmic mystery isn't hiding somewhere distant. It's surrounding us right now. We live inside it. We're drifting through a cosmic desert. Picture this: we live in exile. Our entire galaxy, along with everything we can see around us, exists on the edge of emptiness. We're stranded on the boundary of a vast, dark void, a cosmic desert so enormous that light itself takes 200 million years to cross it. Welcome to the local sheet. This is a colossal wall of galaxies, roughly 300 million light-years wide and 50 million light-years thick. The Milky Way is here. Andromeda is here. And scattered across this thin blade of matter are hundreds more galaxies, all clustered together, like a last stand against the void. But they're not just sitting here passively, they're running. All of these galaxies are fleeing, moving away from the center of the local void at 160 miles per second. That's not the normal cosmic expansion you've heard about. That's extra velocity. That's panic. Here's why. Matter hates voids. Gravity pulls things toward density, toward concentration, toward other stuff. So galaxies that formed in empty spaces experience a relentless tug, away from the emptiness and toward the walls. The local sheet is one of those walls. It's where matter accumulated, as it drained from the void, forming a barrier between two regions of near-total darkness. On one side, the local void stretches 200 million light-years into the black. On the other side, an even larger void stretches even further. We're literally living on the edge of oblivion, and the oblivion is pushing us away. But here's the truly mind-bending part. We're moving through space at 370 miles per second, relative to the cosmic microwave background. That's not one force. That's a symphony of gravitational influences all acting on us simultaneously. The local void is pushing us outward. The massive KBC void is doing the same from another angle. Meanwhile, something called the Shapley concentration, A colossal cluster of galaxies, 650 million light-years away, is pulling us with its gravity. And on the opposite side of the sky, an underdense region called the dipole repeller is shoving us away like a cosmic bully. We are caught in the middle of a tug-of-war between the invisible structures of the universe itself, and this isn't unique to us. Wherever you look in the cosmos, voids create this effect. Galaxies near void boundaries stream outward faster than they should. Distant observers see enhanced redshifts, light stretched and distorted, because galaxies are flowing away from them toward the nearest void boundary. The universe is weeping, draining toward its emptiness. This hierarchy of emptiness and structure, voids within voids, walls within walls, reflects something profound about how the universe was born. In the earliest moments after the Big Bang, tiny density fluctuations rippled across the cosmos at every scale imaginable. Some regions became slightly denser, others became slightly less dense. That's all it took. Over billions of years, those whispers became screams. Small fluctuations grew into galaxies. Larger fluctuations grew into clusters. But voids. Voids grew through evacuation, through relentless drainage. Matter flowed out, and emptiness expanded. The result is a cosmic web of staggering complexity. Structures spanning 6 orders of magnitude, from tiny galactic groups to supervoids larger than anything human minds evolved to comprehend. We live at every level of this hierarchy at once. We're members of the local group. We're residents of the local sheet. We're inhabitants of the KBC void. We're citizens of the Laniakea supercluster. And at every scale, gravity writes our destiny. But beyond the KBC void's boundary, something changes. The gravity strengthens dramatically. The emptiness ends. And whatever awaits us in that direction may very well determine not just where we're going, but where everything is going. The cosmic tug of war, imagine standing in a cosmic arena, caught between 2 titanic forces, pulling you in opposite directions. That's where we are right now. Our entire galactic neighborhood is being dragged through space by an invisible giant. A supercluster so massive, so gravitationally dominant, that it warps the motion of billions of galaxies around it. This monster is called Shapley, and it's winning. Over 8,000 galaxies cluster together in a region spanning roughly 300 million light-years. The total mass? More than 10,000 trillion times heavier than our sun. That's not just a lot of gravity. That's a cosmic vacuum cleaner, pulling everything within range toward its center, and we're being sucked in. Our local group, our corner of the universe, is accelerating toward Shapley at 400 miles per second. That's not metaphorical. That's the actual velocity we're moving through space. Right now, this very moment. But here's where the story gets stranger. On the exact opposite side of the sky, something equally remarkable is shaping our fate. It's called the dipole repeller, and despite its name, it's not pushing us. It's actually the absence of push. In 2017, Israeli physicist Yehuda Hoffman and his colleagues at Hebrew University made a stunning discovery. They found a massive cosmic void, a region so devoid of matter that it might as well be empty space. It's roughly the same distance away as Shapley, but instead of containing thousands of galaxies, it contains almost none. The repeller isn't a force, it's a nothing, and that nothing is reshaping our universe. Think about it this way. Imagine you're on a hill. If you're pulled down one side, you accelerate downward, but if the other side of the hill suddenly vanishes, leaving just air behind you, you accelerate even faster. That's exactly what's happening to us. Shapley pulls. The repeller doesn't push back. Together, they've created a cosmic highway, a gradient in gravitational intensity that channels our entire local group down a preferred direction. We're rolling downhill while the brakes fail. The universe isn't evenly distributed. It has a topology, peaks and valleys in the gravitational landscape. These structures aren't random. They're cosmic highways that guide the flow of billions of galaxies. We travel one of these highways, caught between an attractor and a void, between gravity pulling us forward and the absence of gravity behind us. But mapping this landscape is harder than it sounds. The boundary between a void and normal space doesn't exist as a sharp line. Instead, matter density increases gradually, a slow fade from almost nothing to cosmic average spread across hundreds of millions of light years. Within this transition zone, something remarkable happens. Filaments of galaxies extend into the void like tendrils searching for light. Walls of matter mark the edges, like the rim of a cosmic crater. The exact boundary depends on how you define it, by density threshold or by gravitational properties. The answer isn't obvious. Then came a breakthrough. Astronomers developed a new tool, weak gravitational lensing. When light from distant galaxies passes near a void, that empty region creates less gravitational deflection than normal space. It's like light bending slightly less around thin air than around concrete. By measuring tiny distortions in the shapes of distant galaxies, warped by the gravity of everything between us and them, astronomers can map the invisible matter distribution in the foreground. This includes voids. The early results? They confirmed something unexpected. Voids contain even less matter than we predicted. The universe is emptier in some places than our models suggested. But the real revelation isn't about density. It's about what this emptiness does. At the edge of a void, you're standing at a phase transition, a boundary between two different regimes of cosmic behavior. Inside the void, dark energy wins. The mysterious force that accelerates the expansion of space overwhelms gravitational attraction. Matter streams outward in coherent flows, pushed by the expansion itself. Outside the void, gravity dominates. Matter flows inward, toward overdense regions along cosmic filaments. We live in between. The Milky Way sits on the edge of this cosmic divide, experiencing both influences simultaneously. We're being pulled toward Shapley, while the void behind us fails to pull us back. We exist in a weird, unstable equilibrium, geographically near void center, yet dynamically influenced by external attractors. We live on the edge in multiple senses, and this edge is strange. Galaxies that form inside voids don't behave like other galaxies. Observations confirm a pattern that seems almost impossible. Void galaxies, birth stars, at higher rates than galaxies in normal density regions. They appear younger, bluer, more actively building stellar populations. This shouldn't be true. Voids contain less gas, fewer resources, less material to make stars from. Yet somehow, where matter is scarce, star formation thrives. The universe has one more paradox for us, and we're only beginning to understand it. The universe's quiet corner. Picture this: a galaxy surrounded by nothing. No crowded neighbors to collide with. No gravitational bullies tearing it apart. Logic would suggest such a place should be a cosmic wasteland, a backwater region where galaxies slowly fade into obscurity. But here's the puzzle. These isolated galaxies are thriving. They're outperforming their crowded cousins in ways we didn't expect. The difference comes down to one brutal truth about the universe. Density kills. In galaxy clusters, those dense cosmic cities where billions of galaxies crowd together, violence is the norm. When galaxies pass close to each other, their gravity doesn't politely interact. It tears. Gas gets ripped away by tidal forces and ram pressure. Close encounters ignite explosive bursts of star formation. burning through available fuel in cosmic blinks. Major mergers don't create anything new. They create tombstones. Two spiral galaxies collide and merge into a single elliptical system, exhausted, spent, dead inside. The result? Galaxy clusters become graveyards of old, red, passive systems. Stars that haven't been born in billions of years. Galaxies that stopped growing when your ancestors were still learning to walk. Now turn your attention to the voids, the vast, empty spaces between clusters. Here, something remarkable happens. Nothing violent occurs. Separated by immense distances from any neighbors, void galaxies evolve in solitude. Their gas remains undisturbed. Star formation doesn't explode in destructive bursts. Instead, it proceeds at a steady, moderate pace. Generation after generation, predictable and continuous. These galaxies keep their spiral structures intact, their rotating disks still churning out new stars. They look younger because they are younger. While their cousins in dense environments stopped growing billions of years ago, void galaxies are still building, still reaching toward the future. While the rest of the universe looks backward into age, the pattern is unmistakable. Dense environments are dominated by early-type ellipticals, those passive, ancient systems. Voids? They're full of late-type spirals and irregular galaxies, still active, still young. Intermediate environments show a mix. This relationship, the morphology-density relation, is one of the universe's clearest rules. Where you live determines what you become. And the Milky Way. We're a perfect example of a void dweller, a late-type spiral galaxy with ongoing star formation, evolving peacefully in an underdense environment. We exist in cosmic slow motion. The chemical story deepens this picture. Heavy elements don't appear from nowhere. They're forged inside stars through nuclear fusion, then scattered across space by supernova explosions. Galaxies that have been forming stars continuously accumulate these heavy elements. The longer the star formation, the higher the metallicity. Void galaxies show lower abundances of heavy elements on average, not because they're younger in absolute terms, but because they have less cumulative star formation history. Without major mergers importing pre-enriched gas from other galaxies, void systems build their chemical complexity slowly, patiently, through internal processes alone. Here's where this gets profound. Void galaxies might be windows into the ancient universe itself, because they evolve slowly, because they interact rarely, because they avoid environmental processing. Void galaxies retain characteristics typical of galaxies from billions of years ago. When you study a void galaxy today, you're not looking at some alien oddity. You're looking at what all galaxies looked like before the universe became crowded and violent, before dense environments reshaped everything. Our location in a void doesn't make us special. It makes us typical of an earlier epoch. We live in a pocket where time moves differently, where evolution proceeds at an ancient pace while the rest of the universe rushes ahead. But space is never truly empty. Even in the deepest voids, invisible fields thread through the darkness like the strings of a cosmic loom. Intergalactic magnetic fields, present throughout all cosmic structure. Some were born in the universe's earliest moments. Others were built up gradually through astrophysical processes we're still struggling to understand. These fields reveal fundamental physics, and voids offer the clearest laboratory to study them. With fewer galaxies, less plasma, fewer contaminating effects, the primordial magnetic component stands out more clearly. The signal becomes unmistakable. Our first clues came from the most violent objects in the universe: gamma-ray bursts and distant blazars. These cosmic fireworks emit high-energy photons so powerful They journey across billions of light years to reach us. During that epic journey, something remarkable happens. Those photons occasionally interact with the intergalactic magnetic field, and in that interaction, we glimpse the invisible architecture holding the universe together. The void isn't empty, it's full of secrets we're only beginning to read. The hidden cosmos, magnetism in the void. There's something happening in the emptiest parts of the universe that shouldn't exist, and yet it does. Imagine a cosmic conspiracy of light. High-energy gamma rays travel across billions of light years, only to collide with a phantom. A stray photon from the cosmic microwave background, the ancient afterglow of the Big Bang itself, strikes the gamma ray head-on. In that collision, something extraordinary happens. The gamma ray transforms. It vanishes, replaced by an electron and its mirror image, a positron. These particles don't stay long. They quickly annihilate with other photons, creating brand new gamma rays that scatter in slightly different directions. This cascade repeats again and again, like ripples spreading across a cosmic pond. But here's where it gets interesting. This entire choreography, this intricate dance of particles and light, leaves fingerprints, and astronomers have learned to read them. By measuring how gamma ray patterns get twisted or dimmed as they traverse the universe, scientists can reconstruct something invisible, the magnetic fields that shape them. In 2015, astronomers pointed their telescopes at blazars, the brilliant cores of distant galaxies, whose light had to pass through the vast cosmic voids. These are the true deserts of the universe, regions so empty they seem like nothing at all. But the light told a story. The analysis revealed something astonishing. Even in these voids, even in the absolute emptiest places we know of, magnetic fields exist. The numbers are staggering. We're talking about fields of at least 10 to the negative 17 Gauss. To put that in perspective, Earth's magnetic field, the invisible shield that protects us from solar radiation and lets compass needles point north, measures about half a Gauss. The magnetic field in intergalactic voids is 100 million billion times weaker. That's not just weak. That's cosmically, almost impossibly, incomprehensibly weak. Yet its existence changes everything we thought we knew. Here's the problem. Fields this weak shouldn't exist. They shouldn't be able to exist. The astrophysical engines we know about, supernovas detonating with the force of a billion suns, supermassive black holes tearing at the fabric of space itself, they should erase these signals like a hurricane erases footprints in sand. These fields should have been annihilated, scrambled, destroyed by the universe's violence. Instead, they're organized, structured, nearly uniform across vast distances. That can only mean one thing. They're ancient, primordial, born in the first fractions of a second after the Big Bang, when the universe was so hot and dense that the laws of physics themselves were different. These magnetic fields are cosmic fossils, relics of creation itself. But the story gets even stranger when you look at how they're arranged. In the cosmic filaments, the vast highways of matter that connect galaxy clusters, like threads in a cosmic web, the magnetic fields align like soldiers in formation. They point preferentially along the filament's spine, stretched and sharpened by the cosmic drama that built our universe's structure. But in the voids, in those lonely, empty expanses, the fields tumble randomly, pointing in every direction like a scrambled compass. Why the difference? Picture it this way. As the universe evolved after the Big Bang, matter didn't distribute evenly. Gravity pulled it toward concentrations, draining it from voids toward filaments. As that matter flowed, billions of tons of plasma streaming like rivers of fire, it carried magnetic fields along with it. The shearing and stretching of those flows twisted and amplified the fields, aligning them with the direction of motion. In the filaments, the fields got organized, but in the voids, where the matter flows are gentler and more chaotic, the magnetic fields retained their ancient, primordial randomness. They're still telling us about the universe's first moments. The question is, how did these fields form in the first place? Scientists have proposed several mechanisms. Perhaps they emerged during a phase transition in the infant universe, when forces that were unified suddenly split apart. The electromagnetic force separated from the weak nuclear force in a cosmic cataclysm, and in that chaos, magnetism was born. Or perhaps, and this idea is even stranger, the quantum fluctuations that seeded all the stars and galaxies we see today also seeded magnetism. During cosmic inflation, when the universe expanded faster than the speed of light, tiny quantum whispers were stretched to cosmic scales. Some of those whispers encoded magnetism. The exact strength and structure of these primordial fields depend on precisely when and how this generation occurred. Details we're still trying to understand. And this is where the void observations become crucial. Voids are laboratories. They're the least processed, least modified regions of the universe. Everything else has been heated, compressed, shattered by billions of years of cosmic violence. But voids? They've been largely left alone. The magnetic fields there preserve an almost pristine record of the early universe. By measuring them, we're reading the universe's autobiography, written in its first chapters. These magnetic fields might seem like an obscure curiosity. After all, they're vanishingly weak. But they reshape our understanding of the cosmos in profound ways. They deflect cosmic rays, high-energy particles streaming from supernova explosions and black holes, bending their paths across light years like an invisible maze. They may seed the magnetic fields we find in galaxies, providing the initial spark that galactic dynamos then amplify into the powerful fields we observe today. And they shaped the structure of the intergalactic medium in the early universe, influencing how matter reorganized after the cosmic dark ages, affecting everything from star formation to the ionization state of intergalactic hydrogen. Most profoundly, voids are not empty. Darkness doesn't mean absence. It means hiding. The voids of the universe preserve memories, signals, fingerprints of creation that denser regions have destroyed. They're time capsules, holding the universe's earliest secrets. And those secrets are being revealed by the most unexpected messenger: light that shouldn't exist, and magnetic fields that shouldn't be there. The cold spot mystery. There's a bruise on the universe. It sits in the cosmic microwave background, the ancient light left over from the Big Bang, and it shouldn't be there. Imagine you're looking at a cosmic fingerprint. The universe left one behind, imprinted in radiation that's been traveling toward us for 13.8 billion years. According to our best theories, this fingerprint should be almost perfectly smooth. The tiny variations we do see should follow predictable patterns. Random fluctuations, nothing more. Statistical noise. Background hiss in the signal of creation itself. But the cold spot defies expectations. It's colder than it should be. Darker, and it's massive, spanning a region of sky larger than the full moon. Now, there are three ways to make sense of this cosmic anomaly, and they lead us down very different paths. The first explanation: cosmic bad luck. Maybe the universe just got unlucky. In any random distribution, extreme outliers will eventually appear. Flip a coin enough times and you'll see an improbable streak. The cold spot could be exactly that. A 1 in a million accident written across billions of light years. Unusual, yes, but physically meaningless. Just the universe rolling snake eyes. The second explanation: new physics. But what if it's not an accident? What if the cold spot is a message from the universe's infancy, telling us that inflation, the violent expansion that shaped the cosmos in its first fraction of a second, didn't work the way we thought? Standard inflation predicts nearly perfect randomness in the primordial fluctuation field. But sometimes, in the early universe, fluctuations could deviate from this pattern. More dramatically, more bizarrely, if the cold spot traces one of these extreme deviations, it would reveal entirely new physics operating in those first incomprehensible moments after the Big Bang. It would mean our simplest models of cosmic creation are incomplete. And physicists? They dream of this possibility, because new physics means new truths about reality itself. The third explanation: a cosmic void. But there's another possibility, one that turns our attention outward, toward our own cosmic neighborhood. Picture a photon, a particle of light born in the cosmic microwave background 13.8 billion years ago, traveling directly toward us. Now imagine its journey as crossing through an invisible landscape. Sometimes it enters empty regions of space, vast voids where almost nothing exists. Sometimes it passes through dense clusters of matter. Here's the strange part: empty space and dense space are not equivalent. In our universe, space itself expands, and it expands differently in different places. When a photon climbs out of a gravitational potential well, when it escapes from a region of dense matter, it loses energy. It gets tired. It cools down. Conversely, when a photon tumbles into a well-like region, it gains energy. It heats up. This is the integrated Sachs-Wolf effect. It's gravity's way of reshaping light as it journeys across the cosmos. Now imagine a truly gigantic void, a supervoid so enormous it stretches for over 1 billion light years, a region of space so empty it violates our expectations. Photons passing through such a void would encounter one massive gravitational potential well, losing energy along the entire path. By the time they reach us, they'd be colder, dimmer, and on our cosmic microwave background maps, that region would appear as a dark spot, the hunt for the void. So astronomers did what they always do. They looked. They searched the cosmos for this hypothetical supervoid, aligned with the direction of the cold spot. What they found was complicated. Some surveys detected an underdense region roughly 1 billion light-years away, positioned exactly where theory predicted. They even found the Keenan-Barger-Cowie void lurking in that same neighborhood, a cosmic emptiness waiting in the darkness. But other surveys painted a different picture. They found underdensity, yes, but not enough. Not quite severe enough to fully explain the cold spot through the integrated Sachs-Wolf effect alone. The math didn't quite work. The truth, it seems, lies somewhere in between. The most likely answer: multiple culprits. Perhaps the cold spot isn't caused by just one thing. Perhaps it's a conspiracy, a moderately large void in our cosmic neighborhood, combined with a somewhat rare primordial fluctuation from the universe's birth, conspiring together to create the observed signal. Neither sufficient on its own. But together, they produce the anomaly. This explanation excites researchers because it forces us to reckon with a deeper question. How large can voids actually grow? Our simulations of cosmic structure formation, the computer models where we watch gravity assemble galaxies into the cosmic web, suggest that voids shouldn't exceed certain sizes. Yet if the cold spot traces a supervoid, and if the Keenan-Barger-Cowie void nearby indicates we live inside an even larger underdense region, then perhaps our simulations are wrong. Perhaps voids can grow bigger than we thought. Or perhaps, and this is the radical possibility, gravity itself operates differently than Einstein's equations predict. One anomaly among many. The cold spot, however, doesn't stand alone. It's part of a constellation of cosmic mysteries. There's a slight asymmetry between the northern and southern skies. Anomalous alignments of large-scale fluctuations that seem too organized to be random. A deficit of power at the largest angular scales. The universe appears flatter and more boring at the biggest distances than inflation predicts it should be. Some researchers interpret these as whispers of new physics, hints that our standard model of cosmology requires revision. Others dismiss them as statistical artifacts, patterns we've trained ourselves to see when staring at incomplete data. This is the fundamental tension in modern cosmology. When does a deviation from predictions constitute evidence for unknown physics? And when is it just noise? The Great Voids. If voids as large as supervoids do indeed populate the universe, they would reshape our understanding of cosmic structure. They wouldn't be rare aberrations. They'd be common features of the cosmic architecture, as natural as clouds in Earth's sky. Consider the Bode's Void, discovered in 1981 by Robert Kirshner and his team. It sits 700 million light-years away and spans 330 million light-years across. Initial surveys found only 8 galaxies in a region that, by average density, should contain roughly 2,000. Later observations deepened that count to about 60. Still catastrophically sparse, the void appears almost perfectly spherical, a bubble of nothingness carved into the cosmos. What makes Bode's truly unsettling is its isolation. It doesn't fade gradually into normal space. It exists surrounded by ordinary cosmic structure, with no obvious explanation for its exceptional depth. Did an unusually large primordial fluctuation carve it out? Did multiple smaller voids merge over billions of years, collapsing into one? Or is something else at work? Something we haven't yet imagined. Observations of galaxies orbiting Bode's reveal a striking pattern. Matter fleeing outward, escaping the void's weak gravity. Over billions of years, material has drained away, and with dark energy accelerating cosmic expansion, Bode's continues to empty, growing colder and darker with each passing age. The universe contains other giants. The giant void, stretching 1.3 billion light-years across and sitting 1.5 billion light-years away, dwarfs Bode's. A cosmic ocean of emptiness, reminding us that the universe at its largest scales is not solid matter. It is mostly void, mostly nothing. What the cold spot teaches us. And this is perhaps the deepest lesson of the cold spot. Even in structures we once considered uniform and predictable, irregularities hide. Anomalies whisper. The cosmos we observe is far stranger and more elaborate than our simplest models suggest. The cold spot might be cosmic bad luck. It might be a message from the universe's first moments, revealing physics beyond our current theories. It might be the signature of a supervoid, proof that the universe's emptiness can exceed our wildest expectations. Or it might be something we haven't yet imagined. But one thing is certain. The cold spot reminds us that the universe has not finished teaching us its secrets. They lie waiting in the darkness, hidden in anomalies and voids, waiting for us to look closer, think deeper, and expand the boundaries of what we thought we knew. The universe's greatest mystery, a cosmic Swiss cheese nobody expected. Imagine stepping back from Earth, back from our solar system, back from our galaxy. Keep going. Back billions of light years into the cosmos itself. What you'd discover would shatter everything you thought you knew about the universe's structure. The universe isn't a smooth, evenly distributed sea of galaxies. It's not even close. Scattered throughout the cosmos are cosmic voids, enormous empty regions, some stretching across 1 billion light years. These aren't small pockets. They're vast, yawning chasms that dwarf anything in our solar system by incomprehensible margins. And they're everywhere. A discovery, hidden in plain sight. For decades, astronomers studying distant galaxies noticed something peculiar when they measured how far away these galaxies were. Using their light as a cosmic ruler, a strange pattern emerged. Certain directions showed far fewer galaxies than others. Not a few fewer, dramatically fewer. Galaxy redshift surveys revealed it unmistakably. The universe's map was dotted with enormous empty spaces. One region became famous, the cold spot. Centered roughly 1 billion light-years away, this region stretches across 1 billion light-years of space. It's not truly empty, but it's eerily sparse. Multiple independent studies, using different methods, confirmed the same finding. Fewer galaxies are arranged in this direction than anywhere else we've looked. But here's the twist. Scientists now believe the cold spot might not be a single void at all. Instead, it may be a series of smaller underdensities stacked like a cosmic bullseye. Their combined effect creating one massive gap, and the cold spot isn't alone. A universe built on emptiness. Meet the Eridanus supervoid. 3 billion light-years away, it sprawls across roughly 1 billion light-years. The Sculptor Void haunts our cosmic neighborhood. The Capricornus Void, the Perseus-Pisces Void. The list goes on. Astronomers have now cataloged thousands of these structures. And here's what's truly staggering. Voids occupy roughly 70% of all cosmic volume. The universe isn't mostly filled with galaxies. It's mostly empty. But there's an elegant logic here. This wasn't random chaos. These voids were predicted. When theorists modeled how gravity sculpts the universe over billions of years, starting from the tiniest ripples in the primordial universe, they found the same pattern. Cosmic voids emerging naturally as gravity clustered matter into filaments and galaxy superclusters, leaving vast empty regions behind. Voids aren't mistakes. They're features. A universe of nested emptiness. What makes voids even stranger is their structure. They don't exist in isolation. Smaller voids nest inside larger ones. Filaments of galaxies thread through void space, connecting occasional island clusters of matter. This creates a hierarchy, and it repeats at every scale you examine. Individual galaxy voids measure roughly 10 to 30 million light-years across. Supervoids exceed 1 billion. And in between, every size imaginable. The pattern resembles fractals, the same structure recurring at different scales, like a cosmic Russian doll that never ends. We live inside this hierarchy. We're embedded in voids nested within voids, stretching toward the edge of the observable universe, and likely beyond it. The map makers arrive. But mapping this cosmic architecture has always been nearly impossible. You can't see the entire universe at once. You need precision. You need scale. You need revolution. In 2021, that revolution began. The Dark Energy Spectroscopic Instrument, DESI, switched on at Kitt Peak National Observatory. This instrument is measuring the redshifts of approximately 40 million galaxies and quasars over 5 years, creating the most detailed three-dimensional map of cosmic structure ever attempted. It's looking out to distances exceeding 11 billion light-years, covering 1/3 of the entire sky. DESI isn't just cataloging voids, it's mapping the universe's history. Because when you look at distant galaxies, you're looking backward in time. Each observation reveals how cosmic structure evolved across billions of years. The mystery deepens. In 2025, DESI's early results dropped, and they revealed something unexpected. When astronomers measured baryon acoustic oscillations, subtle patterns in galaxy clustering, left over from the universe's infancy, They found deviations from what standard cosmology predicts. Small deviations, yes, but deviations nonetheless. This could mean several things. Perhaps it's just the local structure around us. Voids and superclusters, warping the measurements like a funhouse mirror. But here's where it gets truly strange. Those deviations might be the first evidence that dark energy itself is changing over time. That the universe's accelerating expansion might not be constant. That the rules governing cosmic expansion might be rewriting themselves. But distinguishing between these possibilities requires analyzing the full DESI dataset with surgical precision. The answer lies ahead. A new eye on the cosmos. DESI isn't working alone. In 2023, the European Space Agency launched the Euclid Space Telescope, humanity's newest cosmic cartographer. Where DESI measures galaxy positions, Euclid employs weak gravitational lensing, using gravity itself as a lens to reveal the distribution of all matter, including the invisible dark matter we cannot see. Here's the power of this approach. Galaxies only trace the locations of ordinary matter, but lensing reveals total matter. By comparing where galaxies cluster to where gravity bends light, astronomers can measure whether galaxies faithfully follow the universe's underlying structure, or whether something stranger is happening. Voids show deficits in both galaxy counts and lensing signals. But the relationship between these deficits is where structure formation theory faces its ultimate test. Do they match as predicted? Or is the universe telling us something we haven't yet understood? The next frontier. The next several years will be pivotal. DESI and Euclid will work in concert, cross-checking each other's findings, building the most complete picture of cosmic structure humanity has ever possessed. We're about to understand voids not as curiosities, but as the dominant features of reality itself. We're about to trace how the universe's emptiness shaped our existence, and we're about to answer one of cosmology's deepest questions. Is the universe evolving in ways we predicted? Or are we missing something fundamental? The answer is waiting in the cosmic void. The universe's greatest mystery might be hiding in our backyard. We're about to witness something extraordinary. Two of the most powerful observatories ever built are coming online, and they're searching for something we've almost completely ignored: emptiness. In the late 2020s, NASA will launch the Nancy Grace Roman Space Telescope. Roman isn't just another space observatory. It's a game changer. It combines sweeping wide-field imaging with infrared spectroscopy, essentially giving us a camera that can see hundreds of millions of galaxies with precision distance measurements. But here's what makes Roman truly revolutionary. It can detect galaxies so faint, so dim, that ground-based telescopes simply give up on them. These are the invisible populations lurking in cosmic voids, the vast, almost empty regions of space that most surveys miss entirely. At nearly the same time, the Vera Rubin Observatory will begin operations in 2025, photographing the entire southern sky repeatedly. And when I say repeatedly, I mean constantly scanning for change. Supernovae explosions, transient cosmic events, distant stellar fireworks. These aren't just beautiful, they're scientific gold. Supernovae serve as cosmic distance markers, measuring the universe's expansion independent of any other method. Together, these telescopes will do something unprecedented: map the structure of cosmic voids with clarity we've never achieved before. They'll answer questions we've been asking for decades. How are voids actually born? Do they grow and evolve as the universe ages? And most importantly, does the massive empty region surrounding us represent some cosmic anomaly, or is it simply ordinary? But here's where this gets strange. The universe isn't random. It's dominated by two invisible forces. Dark matter, 27% of all matter in existence. Is this invisible scaffolding holding galaxies together. Dark energy, the mysterious force pushing the universe apart, fills the remaining void. According to our standard model, gravity follows Einstein's equations precisely. Galaxies cluster around dense regions. Voids remain relatively empty. That's how the cosmos should work. Except there's a problem. The void around us, the KBC void, is massive. Roughly 250 million light-years across. And according to the math, it shouldn't exist. Not here. Not now. Not this large. When physicists ran computer simulations starting from the Big Bang itself, evolving the universe forward with standard gravity and dark matter, they rarely generated voids this enormous in our neighborhood. The probability of finding ourselves inside such a vast empty region, estimates range from roughly 1% down to something far rarer. While unlikely events must happen somewhere in the universe, the fact that we're standing inside one forces us to ask a terrifying question. Is our understanding of gravity fundamentally wrong? This is where things become truly interesting. There's a second mystery, making the void even more perplexing. Astronomers have discovered something called the Hubble tension. The universe appears to be expanding faster than our models predict. The standard explanation doesn't work, but there's an unconventional possibility. What if the void itself is affecting measurements? What if we're inside a region where the universe's expansion rate genuinely differs from the cosmic average? In standard cosmology, structure forms through gravity, pulling matter together. Dense regions collapse and compress. Sparse regions empty out further. It's gravitational instability in action. The rich get richer, the poor get poorer. But to explain the Hubble tension through void dynamics, you'd need voids to grow far deeper and emptier than standard gravity permits. You'd need structure formation to accelerate on massive scales, regions stretching hundreds of millions of light-years across. Standard gravity can't do this. Unless gravity itself works differently than Einstein predicted, modified gravity theories propose something radical. What if gravity's rules change at certain scales? What if, at the massive scales where galaxies form clusters and voids stretch across cosmic distances, gravity operates under different principles? These models suggest that structure actually forms faster on large scales than Einstein's equations allow. Voids would grow deeper. Filaments connecting them would grow denser. The cosmic web would sculpt itself into a more dramatic architecture. For the first time, we have the tools to test this. Roman and Vera Rubin will flood us with data. Millions of faint galaxies, precise distance measurements, direct observations of void populations and their properties, magnetic fields hidden in void regions, gas content, the comparison between empty spaces and the dense filaments connecting them. The answers will reshape everything. Either the KBC void is simply a rare cosmic accident and our understanding of physics remains sound, or we're about to discover that gravity has been playing by rules we never suspected. That dark matter and dark energy might be far stranger and more complex than we imagined. That we've been standing inside evidence of new physics all along. Looking up at the stars, never realizing the void itself was the answer we were searching for. The universe is about to reveal its secrets. We just need to look at the empty space between the galaxies. Does dark matter even exist? We've built our entire understanding of the cosmos on a foundation of invisible stuff. Dark matter, cold, mysterious, utterly undetectable by every instrument we've ever created. It makes up most of the universe's mass, and yet, something isn't quite right. The universe we observe looks messier than our theories predict. Galaxies cluster together more dramatically. Structures stretch across the cosmos in ways that shouldn't be possible if cold, dark matter is the whole story. And this contradiction has forced physicists to ask a dangerous question. What if we've been wrong all along? Enter the NUHDM model. It's a radical idea, but it might just work. Instead of relying entirely on cold dark matter, this framework adds something unexpected: sterile neutrinos. Particles so ghostly, so weakly interactive, that they barely touch normal matter at all. They couple only through gravity, and perhaps through delicate quantum mixing with ordinary neutrinos. These hypothetical particles would have a rest energy of about 11 electron volts. Small, subtle, but potentially revolutionary. Here's the key. This hybrid approach, mixing hot and cold dark matter, matches the patterns we see in the cosmic microwave background radiation, the ancient light from the early universe, and crucially, it allows for the enhanced large-scale structure that pure cold dark matter models predict shouldn't exist. The cosmic web becomes grander, more violent, more textured, just as we observe. But there's a catch. Testing these alternatives against reality is brutally difficult. Then there's modified gravity, an entirely different answer to the same problem. Maybe gravity itself works differently than Einstein imagined. Maybe at cosmic scales, the rules change. These theories make strikingly different predictions than dark matter models. And we have a test case. The Bullet Cluster. Two massive galaxy clusters collided billions of years ago, and the wreckage tells a story. When visible matter smashed together, it interacted violently, heating up, losing energy, getting stripped away by the collision. But gravitational effects, the places where we detect actual mass through gravitational lensing, appear offset from the visible material. Cold, dark matter explains this instantly. The dark matter particles passed right through the collision, barely disturbed, while ordinary matter got torn apart. Modified gravity theories face a nightmare scenario. How do you explain this offset without invoking dark matter? Some models invoke hidden fields or additional components. Others collapse under the weight of observation. They simply cannot account for what the bullet cluster reveals. But here's where it gets genuinely strange. We live inside a cosmic void, an underdense region of space, isolated from neighboring galaxies by vast distances. And this void might be the key to everything. In standard cold dark matter cosmology, voids like this are extraordinarily rare. They shouldn't exist, yet here we are, living inside one. If the void formed naturally within our current understanding of gravity and matter, then the lambda cold dark matter model survives, barely. But if forming this void requires modified gravity to work, if standard physics can't explain it, then we've found evidence for a revolution in fundamental physics. The observations are pouring in. Scientists are measuring void properties with unprecedented precision. They're tracking bulk flows, the way matter moves across cosmic distances. They're refining our measurements of fundamental cosmological parameters. The answer is approaching, and when it arrives, it will reshape physics itself, either confirming our current understanding of gravity and matter, or revealing that something profound, something we haven't even imagined yet, remains missing from our theories. But here's what makes this void uniquely important. It's our home. The Milky Way sits isolated within this underdense region. That isolation affects everything about us. The cosmic ray flux hammering our planet, the properties of the intergalactic medium surrounding us, the rate at which nearby galaxies collide and merge. All of these factors cascade down to influence planetary conditions and biological evolution. Think about cosmic rays, high-energy particles, mostly protons, accelerated to nearly the speed of light by exploding stars and other violent cosmic events. They constantly bombard planetary surfaces. Earth's atmosphere shields us, acting as a protective blanket, but worlds without this shield suffer direct exposure. Too many cosmic rays sterilize surfaces. They strip away atmospheres over geological timescales. They make worlds barren. Galaxies undergoing intense star formation generate torrents of supernovae. These explosions accelerate cosmic rays to lethal levels. Void galaxies, by contrast, form stars at moderate rates. Fewer violent events, potentially reduced cosmic ray backgrounds. That means surfaces might remain habitable longer. Life might flourish more easily here than in crowded galactic neighborhoods. Galaxy mergers tell an even darker story. When two galaxies collide, gravity wrenches them violently apart. Stars and planetary systems get flung across vast distances. Some worlds get ejected entirely, wandering into intergalactic space, orphaned from their home galaxies. Others plunge toward galactic centers where conditions are absolutely catastrophic. Merger-triggered starbursts exhaust gas supplies in mere billions of years. Short-lived massive stars erupt as supernovae. The environment becomes hostile, violent, lethal to life. Our void protects us from this chaos, and that raises the most profound question. Is life more common because we live here, or less common? Does our isolation in this underdense region make Earth a cosmic oasis, a sanctuary for consciousness in a violent universe? Or have we been trapped, cut off from the greater cosmic community? We don't know yet. Scientists have only recently started asking these questions seriously, but the implications are staggering. The void around us, this cosmic mystery, might not just reshape fundamental physics. It might reshape our understanding of our own place in existence. The Loneliest Galaxies, a story of isolation and the origin of worlds. Picture this: galaxies colliding across billions of years, stars ripped from their orbits, gas clouds ignited into violent star formation, planetary systems torn apart by gravitational chaos. For most galaxies in the universe, this is life. Constant mergers, endless catastrophe, an environment so hostile that any planet orbiting through it faces devastation every few 100 million years. But not here, not in the voids. In the vast emptiness between galactic clusters, isolated galaxies drift in profound solitude. They avoid the cosmic car crashes. They evolve in peace. For billions of years, uninterrupted. While their neighbors collide and collide again, void galaxies quietly develop. Stable, serene, almost boring. And in that boredom, something remarkable might emerge. The perfect cradle for life. Yet there's a catch. A cruel cosmic paradox. Imagine the universe's first stars. They contained only hydrogen and helium, the two simplest elements. When these massive stars died in supernovae, they forged something new in their deaths: carbon, oxygen, silicon, iron. The building blocks of worlds. Each generation of stars inherited this enriched material, creating more heavy elements, more diversity, more complexity. In dense galactic clusters, where mergers happen constantly, this chemical enrichment accelerates. Fresh gas from colliding galaxies feeds the stellar furnace. Metal-rich material accumulates rapidly. Rocky planets form readily. But void galaxies? They're starved for interaction. Without frequent mergers, void galaxies can't import fresh fuel. They're forced to recycle their own gas again and again, endlessly managing limited resources. Heavy elements accumulate slowly, so slowly that their metallicity lags behind galaxies swimming in cosmic crowded cities. And here's the problem. Rocky planets don't form easily in metal-poor gas. The materials simply aren't there. So we face an impossible choice. Void galaxies offer stability. Billions of years of peaceful evolution where planets don't get obliterated, but they're starved. of the chemical richness that planets need to exist in the first place. Meanwhile, dense galactic environments provide abundant materials and stellar interactions that continuously recycle and amplify heavy elements. But any world born there faces relentless catastrophe. The first habitable worlds in void galaxies might arrive later than elsewhere, if they arrive at all, without regular mergers to inject new gas, without constant star formation to replenish stellar fuel. A void galaxy's window for creating new stars gradually closes. The furnace dies. No new stars means no new planetary systems. Eventually, the opportunity vanishes entirely. Which effect wins? Stability or starvation? Right now, we don't know. The models are incomplete. The answer depends on details we still don't fully understand. The precise timescales of galaxy evolution, the exact conditions for planet formation, the mysterious requirements for life itself. What we do know, where you're born, matters. Our home, the Milky Way, exists within something called the KBC void, a vast bubble of below-average density stretching billions of light-years across. We live in isolation. We evolved in peace. But was this a blessing or a curse? Maybe we inhabit a rare refuge, a cosmic sanctuary where life flourishes more readily than anywhere else. Or maybe we're stranded in a desert, a relatively dead zone where habitability is harder to achieve. We're just one data point, one galaxy, one story. To know the truth, we need to find life elsewhere. We need to map where it appears, where it clusters, where it's absent. We need to see if habitable worlds concentrate in dense regions or in the quiet voids. Only then will we understand whether the universe teems with life or whether we're nearly alone in a cosmos that's hostile to the very thing we represent. And there's one more wrinkle, one more way isolation reshapes our cosmic destiny. Dark energy is accelerating the universe's expansion everywhere. But inside voids, where matter is thinner, gravity offers less resistance. The expansion accelerates faster here. Space inside the KBC void stretches slightly quicker than space in typical regions. This difference compounds over cosmic time. In the unimaginably distant future, as dark energy dominates everything, this accelerating expansion will continue. Neighboring galaxy clusters will recede faster and faster, redshifting beyond visibility. Eventually, our void will be completely isolated, cut off from the rest of the universe by the expansion itself. We'll be locked inside an event horizon of cosmic proportions. This isn't metaphor. This is mathematics. Dark energy's current density seems trivial, roughly 3 to 7 hydrogen atoms per cubic meter spread across all space. Negligible, invisible. But here's what makes it terrifying. Unlike ordinary matter, dark energy doesn't dilute as the universe expands. Matter gets spread thinner. Its influence weakens. But dark energy? It stays constant. As the cosmos ages and dark energy grows relatively stronger, it will eventually overcome all gravitational binding, except within tightly bound structures like individual galaxies or small galaxy groups. We might already be staring into our long-term future, isolated in our void now because of cosmic density fluctuations, destined to be even more isolated billions of years hence because dark energy will complete what chance began. And in that ultimate isolation, surrounded by redshifted galaxies receding beyond perception, we'll have nothing but ourselves, and the profound question of whether we ever truly weren't alone. The end of everything. Picture this: 2 galaxies locked in a cosmic dance that has lasted for billions of years. The Milky Way and Andromeda, along with dozens of smaller companions, are locked in gravitational embrace. In 3 to 5 billion years, they will collide. Not violently, but inevitably. They will merge into one massive elliptical galaxy, a single titan born from the union of titans. But here's the thing that should terrify you. Almost everything else will disappear. Right now, galaxies surround us, billions upon billions of them, scattered across the observable universe. But the universe is expanding, not just expanding, accelerating. Galaxies are racing away from us faster and faster, pulled apart by dark energy, a force we barely understand. Their light will stretch, redshift into invisibility, and eventually, their new light will never reach us again. They will vanish beyond what physicists call the cosmic horizon. From our perspective, the universe will empty out. The Milky Way Andromeda merger will drift alone. Utterly, completely alone. A single island in an ocean of expanding darkness that grows vaster every passing moment. For a while, star formation will continue. The merger will ignite a frenzy of new stars as the two galaxies collide and compress their gas. But nothing lasts forever. Eventually, all that gas will be burned away or expelled into space. Star formation will stop. The universe will fall silent. Now begins the long, slow fade. Low-mass stars, red dwarfs they're called, burn their fuel with agonizing slowness. They can survive for trillions of years. But massive stars, they burn hot and fast, exhausting their fuel in mere billions of years before exploding as supernovae or collapsing into black holes. Over tens of trillions of years, the merged galaxy will transform. Its population will shift entirely toward the remnants, dim red dwarfs, cooling white dwarfs, and black holes of every size. After about 100 trillion years, the last star will die. Think about that number. 100 trillion years. The universe is currently only 13.8 billion years old. The remaining lifespan of stars stretches ahead for timescales so incomprehensibly vast that human language almost breaks trying to describe them. When the last star finally dies, the galaxy becomes a graveyard. White dwarfs slowly cooling into black dwarfs. Stellar corpses radiating away their final heat into the void. Neutron stars gradually spinning down, their rotation slowing to a crawl, and black holes, those mysterious remnants of dead, massive stars, slowly evaporating through Hawking radiation. A quantum phenomenon where black holes leak away their mass, bit by bit, over unimaginable timescales. Any civilization that survives to this epoch faces an existential crisis, the energy crisis. No fusion, no stars, no conventional power sources remain. Darkness and cold dominate. But the decay continues beyond even that. Some physics theories predict that protons, the fundamental building blocks of all ordinary matter, might not be stable forever. They might decay with half-lives of 10 to the 35th power years or longer. If true, ordinary matter itself gradually disintegrates into radiation. Atoms dissolve, molecules crumble. Everything made of normal matter slowly transforms into pure energy. Black holes dominate what remains. They become the universe's mass budget, but even they don't last. Through Hawking radiation, they evaporate. The most massive black holes take the longest, up to 10 to the 100th power years. That's a 1 followed by 100 zeros, a number so large it dwarfs every other timescale we've discussed. Eventually, in a universe of truly inconceivable age and emptiness, nothing remains. No stars, no planets, no black holes, no structure, only a cold, dark, nearly empty, ever-expanding void, approaching maximum entropy. Heat, death, the ultimate cosmic fate. Here's what's haunting. We're already living in a preview of this distant future. We inhabit a void. Our local group of galaxies is surrounded by relative emptiness. We drift in isolation, while other galaxy clusters recede beyond our horizon. The cosmic expansion is faster here than the universal average. We are already being carried toward the universe's ultimate end state, billions of years before heat death arrives. The darkness surrounding us isn't just empty space between galaxies. It's a harbinger. It's destiny approaching. The future is already here, arriving at our doorstep first. The universe is becoming what we already inhabit. We live inside an expanding void, and we have always been trapped within it. There's another layer to this cosmic tragedy, revealed by general relativity itself. Time doesn't flow uniformly. It's malleable, affected by gravity. On Earth's surface, time moves slightly slower than it does in orbit around us. Not by much. A difference of microseconds, but measurable and real. GPS satellites have to account for it, or their timing would drift, and your navigation would fail. The closer you are to a massive object, the more strongly gravity curves space-time, and the slower time flows relative to areas with weaker gravity. The same principle applies to the entire cosmos. In regions where matter is dense, space-time curves sharply. Time dilates. In voids like ours, where matter is sparse and space-time is relatively flat, time flows faster. We're experiencing time at a different rate than matter in dense regions ever could. We're not just spectators to the universe's fate. We're inhabitants of a void that's teaching us what everything will eventually become. And there's no escape. The universe's hidden clock, deep in the cosmic void, where galaxies scatter like lonely islands in an endless ocean, something extraordinary is happening. Time itself is running faster. Not by much, not in any way you'd notice if you lived there. But over billions of years, the difference becomes staggering. Imagine two clocks placed at opposite ends of the universe. One in the heart of a dense galaxy cluster, suffocating under the weight of countless stars and dark matter, and another floating in the vast emptiness of a cosmic void. As the universe aged from 1 billion years old to today, that clock in the void would have ticked forward 10 to 20 million years faster than the one in the dense cluster. 10 to 20 million years, the same amount of time that separates us from the dinosaurs. This isn't magic, it's Einstein. General relativity tells us that gravity warps time itself. Dense matter bends space-time more severely, and that bending slows time down. In the crowded heart of a galaxy cluster, time moves more slowly. In the lonely expanses of a void, where matter spreads thin, time accelerates. The effect is real. The math checks out. The observations confirm it. But here's where things get interesting. This has profound consequences for how we understand the cosmos. When astronomers observe a distant galaxy, they're looking backward in time. The light we see left that galaxy billions of years ago, and we use that journey to understand cosmic history. But there's a problem we've mostly ignored. That distant galaxy didn't experience time the same way we did. If it formed in a dense cluster, time moved slowly for it. If it grew up in a void, time raced ahead. Two galaxies that formed at the same moment in the cosmic calendar, the same age by our watches, actually experienced vastly different amounts of proper time. One aged faster than the other. One's stars burned brighter and shorter. One's evolution proceeded with a subtle but real head start. This distinction matters more than we thought. When we try to measure the universe's expansion history with precision, when we chase down the mysteries of how fast the universe is accelerating, when we hunt for answers to the Hubble tension that has cosmologists scratching their heads, we're comparing observations made across regions that experienced different amounts of actual time. It's like measuring the age of two people by their calendars while ignoring that one lived in fast motion and the other in slow motion. We're systematically making errors we didn't even know we were making. Most cosmological simulations sweep this under the rug. They track where matter goes, how gravity pulls and pushes, but they ignore the subtle distortion of time across space. Why? Because the effect is small compared to our other uncertainties. But as we enter an era of precision cosmology, where the difference between being right and being wrong is measured in fractions of a percent, we can no longer afford to ignore it. And then quantum mechanics enters the stage. Heisenberg's uncertainty principle creates a deep connection between time and energy. Systems in different gravitational environments, systems experiencing time at different rates, might have different vacuum energy densities. The quantum vacuum itself could be subtly different in a void than in a cluster. Some theoretical physicists whisper something even stranger. What if the fundamental constants of nature, the numbers that define how physics works, what if they changed based on gravitational environment? What if the laws of physics themselves depended on your address in the universe? There's no evidence for this yet, but there are hints, whispers from the data, strange patterns in the deepest voids that deserve scrutiny. And then there's the light. When photons travel through a void, they experience less gravitational deflection than photons traveling through dense regions. Light is bent by massive objects. This is gravitational lensing, one of Einstein's greatest predictions. Galaxy clusters bend light so severely, they create spectacular cosmic mirages. Arcs, multiple images of the same galaxy, light split and reassembled by pure gravity. It's spectacular and confirmed countless times over. But voids do something different. They anti-lens. When light passes through underdense regions, it experiences less pulling, less bending. The photons spread out more than expected. Background galaxies appear subtly fainter and larger than they should. It's the opposite of lensing, a void-shaped hole in the universe's ability to bend light. The effect is weak. Detecting it requires analyzing millions of galaxies, finding tiny statistical patterns hidden in overwhelming noise. But recent surveys have done exactly that. The signal is there. The void lensing effect is real. We're discovering that the universe is far more intricate than we realized. Time flows at different rates. Light bends less where matter is sparse. The laws of physics might whisper different equations in different neighborhoods. We live not in a simple, uniform cosmos, but in a finely textured universe where location, density, and gravitational environment subtly reshape the very fabric of reality. And we're only beginning to read what it says. Picture this. We live in a universe that isn't solid. It's punctured with holes, vast empty voids that dwarf galaxy clusters, the way oceans dwarf islands. And these voids aren't just empty space. They're active. They're alive. They bend light, distort measurements, and reveal themselves through cosmic fingerprints we're only now learning to read. The evidence was staring us in the face all along. Measurements showed it clearly. Voids contain less mass than the space around them. This matched what we saw when counting galaxies. But now we had something more powerful. Independent verification from the physics itself. Two different lines of evidence pointing at the same truth. But the story gets stranger. Imagine a photon, a particle of light, crossing the universe. In a normal cosmos, dominated by matter, gravitational wells stay constant. A photon falls into a potential well, gains energy, then climbs back out, losing exactly what it gained. It arrives unchanged, a perfect cosmic symmetry. But our universe isn't normal. It's driven by dark energy, and dark energy changes everything. As the universe expands, these gravitational wells decay. They weaken. So when a photon falls into a void, a growing absence of matter, It gains energy on the way down. But when it climbs back out, the well is shallower than before. The escape is cheaper. The photon ends up redder than when it started. This is the integrated Sachs-Wolf effect, and it's written into the cosmic microwave background itself. Look at the ancient light surrounding a void, and you'll see it's slightly colder. Look at regions where our gaze passes through dense clusters, and you'll see warmth. The universe leaves its autobiography in radiation. When astronomers correlated these temperature patterns with actual galaxy surveys, the predictions held. The integrated Sachs-Wolf effect was real, and it proved something profound. Dark energy wasn't just a hypothesis. It was reshaping space-time itself, rewriting the rules of cosmic geometry. But here's where things get troubling. We measure how fast the universe is expanding by watching distant supernovae. Type Ia supernovae are cosmic measuring sticks. Their brightness follows precise physics. We compare what we observe to what physics predicts, and boom, we know how far away they are. Simple, elegant. Except it isn't. Light doesn't travel through empty space. It travels through a minefield. Some light gets bent by gravity, magnified or dimmed. Some gets absorbed by dust and reddened. And some gets shifted by the integrated Sachs-Wolf effect. Its spectrum twisted by passing through a universe that's literally changing beneath it. We have to correct for all of this. Carefully, meticulously. But what if we're not correcting properly? What if there's a systematic error hiding in our measurements? Consider this. We live inside a void. Our local corner of the universe is underdense, emptier than average. Light from nearby supernovae travels through our void to reach us. That's more void transit than a typical cosmic sightline. If we apply corrections based on average cosmic density instead of void density, we'd overestimate distances. We'd think those supernovae are farther away than they actually are. And that would make the universe look like it's expanding faster than it really is. It's a mirage, a cosmic illusion hiding in the corrections. Researchers dove deep into this possibility. Could void effects explain the Hubble tension? That nagging discrepancy in expansion measurements? The current consensus? Probably not entirely. The effect exists, but it's too small to be the whole answer. Yet it might contribute. It might tilt the needle. And that matters because every source of systematic error, no matter how small, is a ghost we need to exorcise. Voids don't simply provide empty space. They actively sculpt the universe around them, bending light, shifting spectra, creating mirages in our cosmic distance estimates. Then, in 2022, astronomers found something that shouldn't exist deep in the Bode's void, one of the loneliest places in the known universe. A galaxy appeared on their surveys. They called it Void Galaxy 045, and it was wrong. Most galaxies are recognizable, flattened disks with spiral arms whirling around bright cores, elliptical clouds of old stars stretched by gravity. There's structure, there's form, void. Galaxy 045 is a sphere, perfectly round, no rotation, no spiral arms, no obvious structure beyond the sphere itself. A ball of stars hanging alone in the dark. The first thought was contamination. Maybe light from a distant cluster behind the void had snuck into the catalog. But follow-up observations crushed that hope. Spectroscopy confirmed it was really there, really inside the void, really at the right distance. The galaxy was real, and it was bizarre. Then they looked deeper. At the stars themselves, every single star appeared to be the same age. Not approximately the same age, remarkably, genuinely, almost exactly the same age. They all formed in one explosive burst about 10 billion years ago. Then star formation stopped. Completely. Not a gradual decline, not a slow fade, a cliff. The gas was gone, exhausted, or blown away in that first frantic episode. The galaxy had burned through its entire fuel supply in one go, and then coasted through the cosmos ever since, aging peacefully in the dark. It looked like a globular cluster, those ancient relics that formed in the early universe and have been drifting passively ever since. Except globular clusters are small, dense prisons of a million stars. Void Galaxy 045 is sprawling, solitary, and vast. A cosmic orphan that shouldn't exist in such a desolate place, yet does. The universe keeps surprising us. Just when we think we understand the rules, it shows us something that rewrites them. The universe's greatest mysteries hide in empty space. Picture this, globular clusters. Thousands, maybe millions of stars, all held together in a tight gravitational embrace. Now multiply that. 1 billion times over. That's a galaxy. We've jumped from one scale to something almost incomprehensibly larger. But here's where things get weird. Some galaxies and cosmic voids shouldn't exist the way they do. Our best theories say galaxies form from rotating clouds of gas. As they collapse, they spin faster, like a figure skater pulling in their arms. The cloud flattens into a disk. This is how the Milky Way formed. This is how almost every galaxy forms. It's inevitable, written into the laws of physics itself. And yet, some void galaxies are perfectly spherical, non-rotating, pristine, impossible. How do you make a galaxy that refuses to spin? You can't. Not through normal physics, unless that original cloud had almost zero rotation to begin with. A cosmically unlikely scenario. Or unless another galaxy smashed into it and stripped away all its rotational energy. But in cosmic voids, galaxies are islands separated by unfathomable distances. Collisions are rare. Yet here, these spherical galaxies sit, defying explanation. The mysteries only deepen. Some void galaxies burn impossibly blue. Massive young stars ignite within them, fusing hydrogen at catastrophic rates. They're converting gas into stars faster than they should, faster than their small mass allows. They're squandering their cosmic fuel like a gambler on a final, desperate night. Meanwhile, other void galaxies appear dead, red and ancient. No new stars, no light, nothing. Yet they sit in environments perfectly suited for ongoing star formation. Somehow, they've switched off. They've quit. And we don't know why. Then there are the starburst galaxies. In dense cosmic neighborhoods, galaxy mergers trigger these events. Two galaxies collide, gas funnels toward the center, like water down a drain. Thousands of new stars ignite in a violent cosmic fury. The entire galaxy transforms in millions of years, burning through its gas supply at incomprehensible rates. But starburst galaxies appear more frequently in voids than anywhere else. In the emptiest regions of space, where galaxies sit alone, isolated, untouched. What's triggering them? There are no neighbors to collide with. There are no external forces to disturb them, unless something invisible is at work. What if dark matter streams, threads of invisible matter winding through the cosmic void, occasionally slam into a lone galaxy? The collision shocks the gas, compression ignites a spark, and suddenly, a galaxy that's been dormant for billions of years explodes with stellar birth. It's a hypothesis, nothing more. But it's one possibility in a universe full of unknowns. And the void dwarfs? They're perhaps the strangest of all. These tiny galaxies contain millions of stars instead of billions. Many formed from nearly pristine gas, the primordial hydrogen and helium, left over from the Big Bang, barely touched by nuclear fusion. They're like frozen fossils, primitive systems that may have been drifting through voids since the universe was young. They could be living relics of the ancient cosmos, unchanged for 13 billion years. They could show us how galaxies first formed, what those first building blocks looked like before they merged and grew into the vast systems we see today. But they're so faint, so small. Current surveys miss most of them entirely. We're staring into cosmic voids and seeing almost nothing. And that raises a terrifying question. What else are we missing? What lies in the deepest darkness? Some physicists propose that reality itself is stranger than we imagine. String theory suggests the universe contains more than 3 spatial dimensions. 6, 7, maybe more, curled up so tightly that we can't detect them directly. But they're there, and they matter. The geometry of these hidden dimensions shapes the laws of physics in our observable universe. Change that geometry, and you change everything. The strength of gravity, the mass of particles, the very forces that hold atoms together. String theory proposes 10 to the 500 possible configurations, each one a different universe with different physical laws, an incomprehensible number of possible realities. And we live in just one. But what determines which state our universe occupies? Here's a wild thought. What if the large-scale structure of the cosmos, the way matter clumps and spreads, actually influences these hidden dimensions? When matter concentrates dramatically, space-time itself warps and bends. That curvature might resonate with the compact extra dimensions, shifting their geometry. And cosmic voids represent the most extreme variations in matter distribution. Regions of complete emptiness surrounded by vast walls of galaxies, extreme curvature, maximum distortion. What if voids aren't just empty space? What if they're windows into hidden physics? Cosmic laboratories where the geometry of extra dimensions shifts and changes, revealing glimpses of a reality far stranger than we've dared imagine? We don't know, and that's what makes it extraordinary. The universe's best-kept secret. We've been staring at the cosmos for centuries, confident we understood the rules. The laws of physics are universal. Constants are constant. Gravity behaves the same everywhere. But what if we've been wrong? What if the universe isn't the uniform, predictable place we've always assumed it to be? Deep inside the cosmic voids, those vast, nearly empty deserts between galaxy clusters, something strange might be happening. The vacuum itself could be different there. Not dramatically different. Subtly. Deceptively. The kind of difference that changes everything. Here's the problem. We haven't found any evidence of it. We've measured the fine structure constant, the number that controls how electricity and magnetism work, across billions of light years of cosmic history. It doesn't waver. It stays locked in place to 1 part in 100,000. Gravity does the same. These constants should vary if voids truly are special. They don't. At least, not by anything we can currently detect. But here's what keeps physicists awake at night. Absence of evidence isn't evidence of absence. We're like someone searching a dark forest with a flashlight that only illuminates 3 feet ahead. Just because we haven't seen the monster doesn't mean it isn't there. When extra dimensions enter the picture. Now imagine something radical. What if reality has more dimensions than the 3 we experience? Not as science fiction, as actual physics. Over a century ago, physicists proposed that gravity and electromagnetism, 2 of nature's most fundamental forces, might be unified through hidden dimensions. In these theories, particles can carry momentum through these extra dimensions, these hidden highways. To us, trapped in our 3-dimensional perspective, that hidden momentum looks like electric charge. It looks like a fundamental property of matter. But it's really something moving in a direction we can't perceive. Voids might be gateways to these extra dimensions. Neutral particles drifting through the empty voids could exchange momentum with these hidden realms. The result? Anomalous forces, unexpected behaviors, cosmic particles accelerating in ways physics can't explain. Or consider the brain world scenario. Imagine our entire universe as a thin sheet of paper floating in a higher dimensional room. Everything we know, atoms, light, you, me, exists on that paper. But gravity? Gravity isn't confined to the paper. It seeps into the higher dimensions. It bleeds through the walls. This is why gravity is so pathetically weak compared to other forces. It's diluting itself into spaces we can't even access. In these models, voids would be places where the geometry shifts, where the separation between our universe and these hidden dimensions changes. And wherever that geometry shifts, gravity's strength could fluctuate. Chant the quantum foam. Beneath reality, zoom in closer. Closer than atoms, closer than the nucleus of an atom. Reach down to the Planck scale, about 10 to the negative 35 meters. This is where space and time themselves stop being smooth. They froth and bubble. Quantum fluctuations erupt constantly, a foam of virtual particles winking into existence and vanishing before we can measure them. This quantum chaos shouldn't matter on cosmic scales. Light traveling trillions of miles should be completely indifferent to what's happening. At scales a billion trillion times smaller. But what if it isn't? Photons journeying through voids might experience different quantum turbulence than photons traveling through dense regions where matter dominates. As they cross billions of light years, they accumulate quantum noise, tiny distortions that add up. The light from distant objects should arrive slightly distorted, carrying a fingerprint of the quantum geometry it passed through. Gamma ray bursts are our test. These cosmic explosions flash high-energy photons across the universe in impossibly short bursts. Perfect messengers, perfect probes. By comparing bursts that traveled through known voids to those that didn't, we should be able to spot quantum gravity signatures if they exist. So far, nothing. But the searches continue. The cosmological reckoning. And then there's the uncomfortable truth that cosmologists have been avoiding. The universe doesn't look uniform. Not anymore. Not when we actually measure it carefully. For over a century, we've built everything on the cosmological principle. The assumption that if you zoom out far enough, matter spreads evenly throughout space. No special regions, no preferred directions. This principle isn't just convenient, it's foundational. Without it, the entire architecture of modern cosmology collapses into mathematical chaos. But the data is getting harder to ignore. We live inside the KBC void, a bubble of space so vast it stretches 2 billion light-years across. The entire observable universe extends only 46 billion light-years in radius. Our void occupies a massive fraction of everything we can see. Think about that. We're not in some tiny, insignificant underdensity. We're in a cosmic desert of staggering proportions. And if voids like ours are common, if the universe is actually dominated by these empty regions, with dense filaments scattered between them, like the exception rather than the rule, then everything changes. There would be no universal expansion rate, only local rates, varying from region to region. Cosmic history wouldn't be the same everywhere. Your location in the universe would matter. Your address would dictate the physics. The universe would have genuine structure, real hierarchy, real meaning to the concept of where. We've been assuming the cosmos rolls like clockwork everywhere, identical, impartial. But the evidence whispers something different. The universe might have character. It might have neighborhoods. It might be far stranger than the smooth, featureless ocean we thought we understood. The search continues. Every observation brings us closer to the answer, and every answer we find might shatter the foundations of everything we thought we knew. The universe's hidden secret picture. This, everything you've ever learned about the cosmos, might be built on a comfortable lie. We've always assumed the universe is basically smooth. Sure, galaxies cluster here and there, but zoom out far enough and it all evens out. It's like looking at an ocean from an airplane. The waves disappear. The water looks flat. But what if we're wrong? What if the universe isn't smooth at all? What if it's fundamentally lumpy, jagged, chaotic, and the smoothness we see is just an illusion? An optical trick created by our limited perspective? Here's the problem. We can't test this directly. Our observations stop at the cosmic horizon, the edge of what light from the Big Bang has had time to reach us. Beyond that boundary, anything goes. Physics becomes pure speculation, yet recent theoretical work suggests something radical. What if the universe is fractal? In a fractal universe, structure repeats at every scale. Galaxies cluster around superclusters, which cluster around even larger structures, which cluster around structures larger still, and this pattern never stops. There's no magical distance where everything suddenly becomes uniform. The universe would be lumpy all the way up, forever. And here's what's wild. Galaxies surveys are showing hints of this. Real data. Fractal behavior appears at scales larger than anyone expected. The transition to smoothness, if it exists at all, doesn't happen until you reach 1 to 2 billion light-years across. That's roughly the size of the biggest voids and filaments in space. Coincidence? Or are we looking at something fundamental? Some researchers think smooth universe is just an assumption we've made, an assumption we never questioned. Our observational window is so tiny compared to the cosmos that we might be completely blind to a deeper reality hiding just beyond our reach. If this is true, everything changes. The equations that describe cosmic expansion, the Friedmann equations, assume the universe is homogeneous, uniform, smooth. They're elegant. They work beautifully. But they might only work because we've rigged the problem from the start. The moment you try to solve Einstein's equations for a genuinely lumpy, non-uniform universe, the mathematics explodes. It becomes nearly impossible. Researchers have built toy models, Swiss cheese universes with spherical voids carved into expanding space. Lindquist-Wheeler models, that tile space with identical clumps of matter. These models capture some real features, but they're still simplifications. Realistic in homogeneous cosmologies? That's still an open frontier. Physicists are still wrestling with it. Now here's where it gets personal. Our solar system sits near the center of a colossal void, a vast bubble of emptiness spanning hundreds of millions of light-years. Why are we here? Think about it. If observers need galaxies to exist, if galaxies are necessary for life to emerge, then observers will only find themselves in regions where galaxies actually formed. Voids contain fewer galaxies than average, so statistically, observers should be less likely to emerge near void centers. And yet, here we are. We could be phenomenally lucky. A cosmic coincidence. 1 in a billion throw of the dice. Or maybe voids aren't hostile to life. Maybe isolation is actually an advantage. Perhaps void regions, cut off from the violent collisions and cosmic catastrophes that ravage denser areas, provide a sanctuary for life to evolve. Maybe the silence and solitude of empty space are exactly what developing worlds need. Steady, quiet evolution instead of constant cosmic bombardment. There's another possibility, one that sounds like science fiction but deserves serious consideration. What if the universe is a simulation? Think about it from the simulator's perspective. Computing power is finite. Why waste resources rendering the entire cosmos in perfect detail? Why calculate every atom in a distant galaxy you'll never see? Instead, optimize. Compute only what the observer can perceive, in high fidelity. Make everything else simple, generic, low resolution. If you place a simulated observer in a void, in an empty region of space, you dramatically reduce the computational load. Nearby galaxies? Few and far between. The vast empty spaces around them? Almost nothing. Minimal structure. These could be represented with almost no computational effort compared to the dense, complex filaments of galaxies elsewhere. From a simulation efficiency standpoint, voids are ideal. They're the cheapest real estate in the cosmos. This means we should expect to find ourselves exactly where we are. In underdense regions, surrounded by emptiness, watching the distant light of a universe that might be far more complex than we can ever see. The argument remains deeply speculative, untestable with our current tools, possibly unfalsifiable forever. But it reveals something profound. Our position in space poses questions that conventional physics alone cannot answer. We live in darkness, and the reasons why might transcend astronomy entirely.